Yes, sure. Can you see my screen?
I can.
Yes.
Okay, so good morning, good afternoon, and good evening, all my audience. Yeah, this is what happens when it's an international workshop. We have people from everywhere. So for those who just joined our workshop, I will just give a brief introduction. LEAP workshop is a 5-day workshop, consists of 14 different sessions. You are welcome and invited to join any of the sessions. So we will still have some sessions tomorrow and on Friday. And in each session, we may have some keynote speaker, or panel discussion, open discussion, or breakout sessions, and social breaks. Here, I would like to say that between two sessions, we have a break, either half an hour or 1 hour. During break, we will have some breakout rooms. You can join any of the room, just chat with other researchers or do some networking, or just catch up with some friends you haven't seen for a long time. And feel free to bring your coffee, your lunch, or your snacks in the breakout social sessions. And another thing is that this workshop is considered as an open to public workshop, which means all the information included in your presentation, discussion must be publicly available before this meeting. If you have sent me your slides before, I think you are good to go, because we posted the slides in our NTL conference page. If you haven't do so, make sure that your presentation or your discussion or the information that you have presented before or published in some data or report. Another thing is that the entire workshop will be recorded. This is because we are going to write a technical note based on the discussions, which will be available to all the audience when it's available. And also the recorded video will be posted in YouTube as well. I will send the link to everyone when it's ready to go. And we suggest you to turn on your camera during talking or during the discussion. And since we have many participants online at the same time, we suggest you to mute yourself except when you are talking. And you can post your questions in chat during the presentations, or you can ask your questions after they finish the presentations. Feel free to mute or unmute yourself during the discussion. I think that's all. Dave, you can take it away.
All right, thanks, Nana. So as Nana showed, today our first session will be on paths to commercialization, and then we'll have a session following that on controls. And finally, at the end of the day, we'll have an open discussion and conclusions. We'll try to wrap everything up, and I hope that everybody can participate, give us their ideas. So to start things off, I'd like to introduce the session chair for our commercialization track here. Dr. David Tu is a program director at ARPA-E, the Advanced Research Projects Agency Energy. So Dave, if I say anything wrong, you just have to jump in and correct me. So Dave has he worked for 19 years at United Technologies in fuel cells, turbines, combustion, and now at ARPA-E, even internal combustion engines. So he's an expert at systems integration and cycle analysis. So and with that, Dr. Tu, I will turn it over to you to get this session started. So.
Great. Well, thank you very much for the introduction, Dave. Can you hear me?
Yep.
Okay, great. And hopefully you can see my slides. They're coming up.
Okay.
Interesting. Oh, there we go. Whoops.
There.
Of course, I just flipped them. Shoot.
Well, actually, you had it good.
Yep. Yeah.
Still
Yeah.
before.
Yeah. It's a little bit slow. Sorry about that.
Okay, no problem.
So thank you very much for today. So today's session is a panel discussion on paths to commercialization for integrated energy systems. I'm just going to do a quick 5-minute introduction and then turn it over to our panelists to give a summary of their work at their organizations in the light of paths to commercialization. If you have specific questions about their presentations, please do put them in the chat or ask them, and we'll have also an opportunity for more open discussion at the end. So just a quick few words myself in terms of what we're doing at RP that's related and why I think this is important. So certainly in order to commercialize these technologies, we need an attractive commercial value proposition. And I think that we all know that this is really driven by our climate challenge. In terms of, and this is just an article or a figure from the New York Times even last week, talking about where we were several years ago in terms of global warming potential by 2100, where we are today, where we've promised to be, and where we need to get to in order to really mitigate some of the most severe impacts of climate challenge. And certainly we have a lot of technology work to do to get from where we think we are to where we need to be. But I think one of the significant challenges we have associated with that is that fuels are going to be very difficult to fully eliminate from our energy system, particularly for transportation applications like aviation, maritime, and even for stationary power generation in very remote regions where there's just not a lot of renewable electricity available. But those future fuels really must be carbon neutral, I think many of us believe. And because of that, they're likely to be higher cost because we actually have to make them from CO2, water, and renewable electricity. And also, I think at this point, it's really not clear, I think in a lot of applications, what the fuel of choice for the future is going to be. There's lots of uncertainty. We talk about hydrogen, synthetic aviation fuel, ammonia, ethanol, methanol, many options in the future, and really the future is coming very quickly. One downside to a lot of these fuels is the fact that many of them are potentially very heavy, meaning they're not very energy dense in some cases on a volumetric or a mass basis. And what that means, and coupled with higher cost, is that certainly for transportation applications, ultra high efficiency is going to be absolutely critical, or even more critical than it is today for transportation value propositions. And I already mentioned the importance of fuel flexibility for future fuel conversion systems because of the uncertainty. And I think ultra high efficiency and fuel flexibility are certainly key characteristics of hybrid systems and systems that employ solid oxide fuel cells with reformers. At RPE, we have a couple of programs that are really supporting the development of these types of systems. One is Integrate, and we've got 3 PIs for Integrate, in addition to Dave, that are going to talk about some of their work. We also have the REACH program, which is focused on aviation applications. Again, ultra high efficiency, carbon neutral fuel conversion systems for aviation. As I mentioned, future fuels will need to be renewable, and we need to produce them which means we need to produce them in a carbon neutral way. And certainly that opens up another, I'd say, commercialization opportunity for a lot of the technologies that we're developing for power generation purposes that can also be used in reverse mode as electrolyzers for fuel generation purposes with renewable electricity. And I think that's an important aspect of the value proposition for the technologies that we're developing to consider going forward. A couple of words about Integrate, and we're already late. High efficiency fuel to electric power conversion system, trying to leverage synergies. The goal is high efficiency at an attractive cost to enable commercial adoption. We're also, with the REACH program, we moved from not just worrying about efficiency and cost, but also worrying about propulsion system weight. This is cruise specific power. This is a very lightweight propulsion system, a very high specific power. These are payload contours. And certainly we want high efficiency at an attractive weight from a fuel, from an aircraft performance standpoint. Our REACH systems are going to be wonderfully efficient, we hope, in a year or two when we actually demonstrate them. The challenge is, while we're not focused on the weight, they're going to be very, very heavy. Hopefully within the REACH program, we're going to maybe sacrifice some efficiency, but hopefully achieve substantial increases in the specific power, which makes them potentially very attractive for aviation applications. Certainly, if we move from synthetic aviation fuel to things like ethanol or things like ammonia, we need substantial increases in specific power and or efficiency to achieve comparable aircraft performance, or we have to sacrifice aircraft performance, which may be a price that we need to pay. With that, what I'd like to do is actually turn the floor over to our Integrate PIs. First of all, Scott Swartz at Nexaris, who's going to talk about Nexaris's commercialization journey. And Scott, the floor is yours, although we probably have to transition slides. Are you there, Scott? I guess I saw Gene.
I don't see Scott on the list.
Yeah,
I
I
know
will.
Gene is-
I am not sure. I will see if I can get him on the line. I see
Okay.
he's in a call. I assumed it was here. I will call him.
Okay. Well, Rob, could we jump to you instead? I know that you're on.
Sure.
Sorry to catch you off guard. I know you had a very early start. You were an hour early, and sorry about the Outlook time zone conversion issue.
Yeah.
We appreciate the eagerness to be ready at 6 a.m.
Yeah.
Mountain time.
Let's see, make sure I can get this. All right, how's that? Can you see the full screen view?
Yes, interesting.
Presentation mode, you can see?
Yep.
Okay. All right, I'll get started. Thank you, Dave, for the introduction. My name is Rob Braun. I'm in the Department of Mechanical Engineering at the Colorado School of Mines. We've been working on this Integrate project, which involves hybridizing a solid oxide fuel cell with an internal combustion engine for stationary applications. The opportunity and market drivers are fairly well known, but I'm going to borrow from the old ARPA-E Rebels FOA, which had a nice plot of installed cost and efficiency of various distributed generation technologies versus the size of the system. And you can see micro turbines in the red. You can see reciprocating engines and gas turbines and so forth. And then there's a fairly large gap you can see in terms of the installed cost at the lower system sizes, as well as in efficiencies. And our project is targeting high efficiency and low cost. And there's a fairly significant DG market, both domestically in the US and abroad internationally. But there are other drivers too, and that's supporting electrification of the transportation sector by being able to ramp up and down and do variable energy resource firming, reducing net carbon emissions. And so we need these flexible power generators. But there's frankly not that many or any really that are available at efficiencies greater than 50% and installed costs less than $2,000 per kilowatt. So our vision here is to drive both a radically lower cost and an ultra high efficiency fuel flexible hybrid power generator in roughly the 100 to 1 megawatt class distributed generation applications. The synergistic benefits are, as previously stated, in terms of supporting electrification, but also including the transportation sector, distributed generation and stationary applications. And there is a CO2 emission advantage compared to other technologies. If you're operating from natural gas, you can see 50% greater than your traditional combustion turbines and appreciable advantages over other high efficiency stationary engines and other fuel cell types. In the US and I think abroad as well, we're certainly noticing there's a fair amount of interest in already banning the use of natural gas in various cities and municipalities. Skipping natural gas perhaps as a transition fuel. Whether that really becomes possible or not is unknown, but we're targeting this system to also be fuel flexible in terms of hydrogen ready and operating off of renewable biogas and biomethane. So the concept is really to take a metal supported intermediate temperature solid oxide fuel cell stack and marry it with a bottoming diesel derived internal combustion engine which will take depleted fuel from the fuel cell, oxidize it, and essentially be like a combustor that also makes electric power, which can then go and offset all the parasitic powers in the plant and provide some net power so that we get overall a high efficiency system. The intermediate cell technology is one nice advantage of this system because it improves the thermal management. It lowers air preheater duties, lowers the service temperatures of the heat exchangers and so forth. We're also going to be pressurizing the system, which will increase the power density of the stack and drive lower costs there as well. And because we're essentially burning H2 and residual H2 and CO in the engine, there's simple after treatment for low engine emissions. So the vision perhaps is shown in this rendered image, which has some pressurized SOFC stacks. It's got engines and rotating equipment driven off of the engine. The rotating equipment is envisioned to be positive displacement, so not centrifugal machines, in part because there's ease of control. Often IC engines do have better part load performance as well. Right now we're targeting under $1,000 per kilowatt and around 7.5 US cents per kilowatt hour on the levelized cost of electricity. There's some other interesting features that are ongoing in this as well, including high efficiency BOP development. And we've been working on first generation prototyping, and in a second phase, we're working on the second generation balance of plant equipment. So the team consists of the Colorado School of Mine, which is kind of leading the prototype development in the systems control and some of the techno-economic analysis, working on packaging these series stacks into power modules. And then our other partners at Colorado State, they're quite adept at working with all different kinds of alternative fuels on engines. They also have a microgrid there, and we'll be installing the prototype into their facility. Kohler Power Systems is the commercialization partner. They're developing and giving us the engines and helping us with the design modifications. They also have a lot of high efficiency alternator and inverter development activities, which I'll touch on briefly later. And then Air Squared in Colorado is providing positive displacement scroll machinery in the plant. And this is really a 3-year effort on the demonstration portion. We had 2 years of design and some first prototyping of units. And now we've begun the second phase, and we're here in year 3 working on design and build of a 30 to 40 kilowatt module. And then in subsequent years, we'll be testing the modules and integrating the BOP, and then trying to get 9 months to a year of system testing down. If we look at some of the performance and cost projections by end of the system demonstration, many of the commercialization targets we think will be met. It's TRL6, certainly perhaps a little bit beyond. In this spider chart here, if you view the red as kind of some of the targets around capital cost, O&M, power density, efficiency, and so forth, the blue is where we see ourselves in this first unit at the end of this program. Our objectives will be also, of course, to increase power densities and lower the O&M. But some of these numbers are, of course, without having built and tested all of it. Like O&M, those targets may be better than we're showing here. Hard to say at this juncture, but these are some of our best guesses at this point. In terms of a roadmap, we started working on this with at least the system concept and topology back in 2017. Got funding through ARPA-E in 2018. Intellectual property and things on the high efficiency inverter. And prototyping of that unit, and prototyping of the scroll BOP, and then here in 2021 we're beginning the next phase, where as indicated, our ultimate goal is to get to this 80 to 100 kilowatt demonstrator unit, and then on-ramp that into the Kohler Power Systems product development process. The multi-stack module development, of course, the fuel cells is the heart of the system. So we've been testing in our pressurized test facility at the Colorado Fuel Cell Center at the School of Mines here in Golden, a 5 kilowatt, what we call a stack test module, characterizing it, and then looking at how it performs under pressure for different kinds of fuel compositions. And then ultimately designing a package unit that will put about 12 of these stacks into a multi-stack module vessel. And we've been working on that most recently. The concept, this is a higher detail flow sheet, perhaps, than I've shown in the past, but the basic idea is we have natural gas. It will mix with some recycle to get the right steam to carbon ratio, do some preheating, deliver it to a fuel cell stack. On the air side, it's shown as mounted with the engine. That means the speed of the engine has to be matched to the speed of the scroll machinery. That's one approach, certainly not the only approach. Anyway, pressurizing up to 3 bar, we preheat, deliver the air to the SOFC and do recuperative heat recovery and expansion. Getting over 71% efficiency in this configuration, but there's just a lot to think about when you do the integration of any energy conversion technology like this. Design pressure, fuel utilization, how good are the stacks that you're going to get off the manufacturing line? Can you design for those uncertainties? Airflow requirements, how much excess air do you need for the thermal management, and other things like heat exchanger effectiveness, what are economic ones you can get, and then things we don't always think about initially when we write papers in academic ventures is things like heat losses throughout the plant, and you've got to be careful on how you do that because that can add up. When you take all those into consideration, you do get an uncertainty range on the efficiency. We think that is tightened around 96 to 72%. Some of these illustrations are just to give you a little flavor for how these things look in terms of, what are the trades? And, one of the trades is fuel utilization. One of the trades are, how good of an tail gas engine in terms of its efficiency on what's really a low calorific value fuel gas. How well can you do with that engine affects the system efficiency. And of course, when you look at the space of utilization and system efficiency, you can see there are many different possibilities which allow you to get better than 70% efficiency, for example. When you look at things like power density, now that enters a new dimension, and that adds a certain cost flavor. So if you look at things like stack pressure, we think you need to be somewhere between 3 to 4 bars, and your utilization, for example, needs to probably be closer to 83 or 84% to reach higher power densities with these kinds of stacks. On the tail gas engine development, our partners at CSU have achieved a 31% efficiency so far in the phase 1, working off a simulated anode tail gas. The next phase is to get that efficiency up to 35%. They'll be working on engine geometry changes and of course, ignition timing in an effort to reach those efficiencies. We are also working on an ultra low-cost, high-efficiency inverter. This inverter may be one of the jewels in this program. It's greater than 98% efficiency. Right now, the capital cost looks like it's going to be less than $90 per kilowatt. So if you do any cost analysis and you look at fuel cell inverters, the numbers are often 150 to 250, and our view is also, after looking at the photovoltaic side, those numbers are just not right, and we think those numbers are going to be south of $100 a kilowatt. Anyway, here you can see some of the inverter performance characteristics as a function of power. The whole system in a prototype, in a test facility, this footprint shown here is much larger than you'd see a packaged unit, but For scale, here you can see a person standing with some supporting equipment for the facility in terms of nitrogen and purge gases, pressure vessel where, you know, roughly 100 kilowatts of stack will go. And then you've got some of the rotating equipment, heat exchangers and so forth, and power conditioning behind the vessel. The top view is shown here. So in this first effort, we demonstrated the engine, pressurized testing of the series stacks. The efficiency targets for the scroll compressor were met. They do have some challenges they're working on in terms of moving to a liquid-cooled scroll compressor design to boost the efficiency even further. And in phase two, we're very much focused on actually the procurement, the build, the integration, and the controls of the demonstration system. When we look to things like tech to market, you know, where are these things going to go? It's hardly a new consideration to think about fuel cell CHP systems in the marketplace. People have been looking at that for over 20 years now. Often what you find is you need high spark spreads. In places like San Francisco and Manhattan in the US seem like they're always the best places to put them, but of course that's a fairly limited market. But as you get higher efficiency and lower costs, other applications begin to open up, and there are critical loads, for example, at data centers, hospitals, and so forth. And if you look at some of the competing technology characteristics, you know, we think with the efficiency ranges and the capital cost targets, you know, we think we're going to compete well. This number here for SOFCs, this is a Bloom Energy taken out of one of their quarterly reports. Actually, it's a little dated. This number is more like 25. Yeah, no, maybe that's about right. I think they're at $2,500 on cost and $3,800 on suggested selling price. In any case, the last thing I would show before I depart in my time here today is we've also been looking at some application studies. So it's one thing to throw together some capital costs and levelized costs, and it's another to see, well, how is it really going to perform against the competition? In a different project we've been working on through the Advanced Manufacturing Office, we've been helping NREL build out their REOPT Lite tool, which incorporates now CHP technologies along with renewable technologies. So PV, wind, batteries, and then a whole host of CHP technologies. So as a part of this process, we started dropping in SOFC and in our hybrid system characteristics into some analysis. And I have some preliminary results I can show. But they are preliminary. We've got a lot more analysis to do. But if you look at something like a data center, which has loads over the course of the year, it's fairly stable. Yeah, there's some dips, but over the course of the year, it hangs near 1 to 1.2 megawatts for this particular data center. Very low thermal to electric ratios, which would match high efficiency systems. And so when we look at implementing the characteristics of different prime movers, versus at what we might call a generic SOFC in this hybrid system. And the generic is based on some public literature, for example. We see that in a number of cases, the hybrid systems without renewable energy will offer decent payback periods of less than 5, high internal rate of return. And then when you start hybridizing with things like photovoltaics, if you were to have only a PV system to hit this data center load, you'd want to install about 2.2 megawatts. In a hybrid system, you'd only need about 1.1 megawatt. But if you're going to hybridize it with PV, it shows us there is shared space. The optimizer likes to pick both of the technologies. And so we don't see necessarily competition between CHP, PV. We see synergy opportunities. So that's my talk in sum. I'd like to acknowledge all the folks. This is only a partial listing of the postdocs, research engineers, grad students, but of course, all the co-investigators. It's a big team, and it's an exciting project. Thanks for your time.
It was great, Rob. Thank you very much. And if anybody has, specific questions, please do type them in the chat, and we'll just acknowledge you and ask you to ask them. One question I do have about some of the comparisons you were doing with alternative energy systems. Did you consider PV with storage, like battery storage, as well as a potential competition for PV and a hybrid system?
Yeah, and I didn't show it here.
Okay.
But yeah, you'll see it eventually, Dave.
Okay.
But yeah, I just for sake, there's just a lot of data on this chart, so I didn't want to keep adding more. But yeah,
Okay.
these systems, the renewable system has batteries in it.
Does. Okay. Okay. And Rory, do you want to go ahead and unmute yourself and ask your question?
I noticed in the diagrams, and I may have seen it incorrectly, that the anode and cathode are coming out separately in the stack to two different expansion devices, one through the ICE engine and the other through the, I guess, turbocharger portion.
Yep. Mm-hmm.
I was just wondering, have you evaluated any pressure differences between the anode and cathode streams that may be high frequency between the two technologies that they're exiting through, and potentially low frequency oscillations in pressure?
Yeah, we'll see that when we do the simulation. They have the opportunity to be connected in terms of mixing the gases to provide a common pressure point. We may do that, but right now our cross pressure differential control is so tight. It's actually fabulous with the way we've designed the unit inside the pressure vessel and the control we have on it, that it's not that big of a concern yet. If it proves to be, we have some alternative options to mix the two gases to provide a common point of pressure.
Okay, thank you.
Okay, well, thanks, Rob. That was great. Certainly excited to see the hardware coming closer and hopefully a system demonstration in the next couple of years. So very exciting.
Just a quick question. This has been Corpening. The economic analysis that you were showing there, is that based on meeting cost targets for the program, or is that based on some other estimation of costs?
Bottom up costing.
Okay.
So you're talking about capital costing?
Yeah, yes.
And
yeah,
actually,
it's bottom up costing. Where it is relative to the target, kind of depends. If you look at supply chain now, cost might be likely different. But in any case, it's all based on 1,000 to 10,000 unit per year volumes.
and I'm sorry, I missed the raised hands earlier. I apologize, Ben. And Harish, would you like to ask your question?
Sure, just a quick question on the inverter that's developed by Kohler. So it looks like it's a dual input inverter which can take inputs from the alternator and the fuel cell. And can you just comment on the inverter design itself and if it's any different from something Kohler would already have?
Yeah, so it has multiple inputs. That's true. It takes the DC out of the alternator and also takes the fuel cell input. And it's also configured to let us control current in a number of different ways on different parts of this of the stack module, if you will. So it's a very flexible device.
Okay, that was great. Thank you, Rob, and thank you for all the great questions. Scott, I see that you're on. Maybe we could move to you at this point.
Yeah, I'm sorry about that, Dave.
No, that's okay. No problem.
I wasn't reading my calendar properly.
No problem at all.
And,
Yep. Says you're the presenter, and we can see the
Saying the wrong
presenter
way.
view, so you may want to swap displays.
Bear with me.
I want to swap displays again.
Oh,
Yeah, Scott,
there you go.
there you go.
Or duplicate either
There,
one.
is that better?
Looks perfect.
Great. Sorry about that. Hey, my name is Scott Swartz, and I don't read calendars very well. I'm also a co-founder and the Chief Technology Officer of Nexaris. I'm glad to be speaking with you today virtually. I would like to thank Dave too for inviting me to participate on this panel. I'll give a short intro on Nexaris, discuss our commercialization approach and our journey, and then I will describe our ARPA-E Integrate project, which was my ticket onto this panel. If I may, I'd like to introduce Nexaris. We were founded in 1994. Some of you may remember us as Nextech Materials. We changed our name to Nexaris in 2015. We work on technologies at the intersection of energy and the environment, and we develop and offer products in the areas of sensors, batteries, catalysts, and solid oxide fuel cells. We have a people-first culture, and we seek the brightest and most passionate team members to solve challenging problems and to help us grow our business. We have grown quite a bit in the last 3 years, and we're now up to about 60 team members. Some of you may know us through our fuel cell materials division, where we make and sell materials and components to OEMs and R&D organizations in solid oxide fuel cell field. And we recently launched lithium-ion battery safety sensors through our Lion Tamer brand. I'd like to give a little bit of a flavor of our commercialization journey through the lens of a small high technology company. We have a long and rich heritage in solid oxide fuel cell technology. We founded the company with a focus in this field, and we have evolved into one of the leading materials and technology providers in the SOFC space. Our approach to commercialization of SOFC and other technologies is outlined on this slide. It all starts with our team, and we're extremely fortunate to have a great team and a lot of long tenured technical staff members. Collaboration is also a key component of our technology development approach, and we have a long history of collaboration from our humble beginnings to where we are today. We have leveraged government funding to steadily advance our solid oxide fuel cell technology while seeking product development opportunities in nearer term markets in fields like catalysts and sensors. We use a stage gate process for product development, and we engage with customers early in the process. We strive not to build a bridge to nowhere, and customer input is essential for this. And we remain privately owned. We've grown our business by reinvesting profits in facilities, capabilities, IR&D, and product development. So here's probably a very complicated but yet very simplified chart showing the evolution of Nexaris in the solid oxide fuel cell space. I mentioned earlier we were founded in 1994 and almost immediately initiated work on solid oxide fuel cell materials development. We initiated our cell development work in 2001 and stack development in 2006. We started working on interconnect coatings for improving stack durability in 2010. We established a military purpose stack design. This is where we needed to adapt our stacks to achieve high power density and sulfur tolerance. This was done we started this work in 2014. We have steadily advanced this technology and most recently via TRL4 and TRL5 demonstrations in the past few years. Our ARPA Integrate project was started in 2018, and leveraging the stack we developed on this project, we initiated our work in high temperature electrolysis last year. And just to show that along the way, our goal was to launch products and start that journey of commercializing. And so we launched fuel cell materials in 2000 at the very early stages of the solid oxide fuel cell industry. And we started just selling cathode powders, and we then grew that product list through planar cells. We launched our planar cell product in 2005. And then we also sell test equipment and a variety of different products. We have we sell globally and have a worldwide customer base. And we also launched our interconnect coating technology in about the 2016 timeframe. We've coated more than 20,000 interconnects for a dozen fuel cell companies. And the coating technology ultimately was licensed non-exclusively and transferred to a Fortune 500 global OEM. And this is just another chart showing some of the work that we've been doing in the field of sensors. We actually started the sensor development work in the 2000 timeframe, 2001, with some projects where we were developing sensors for fuel cell applications. We ultimately learned a lot about the sensor business and developed a lot of different sensing capabilities. But the market, back then really wasn't ready for some of the sensors we were developing. So we sort of shifted a little bit. We initiated work on NOx sensors in about the 2006 timeframe. We continued to develop those NOx sensors and we're actually quite close to getting some key demonstrations done with OEMs. And in 2007, we initiated work on a hydrogen sensor product. We launched that product in 2010. But with that same platform, starting in about 2010, we started developing sensors to detect off-gas species of lithium-ion batteries. We were able to detect these off-gases very early in the process of a battery fire, well before a battery fire, and in time to actually do something about a pending fire. So we call this the Lion Tamer. We launched this Lion Tamer product in 2017, and we signed a joint venture agreement with Honeywell to commercialize the technology further in 2020. You should check it out. It's on our website. I'm sure you'll find it interesting. Good stuff. Now I'd talk to you a little bit about our hybrid power system work that we're doing on Dave's Integrate program. We're working with two companies in this project, C0 in Fort Collins, Colorado, and Brayton Energy in Hampton, Virginia. And our goal, I think Rob just gave a pretty good background on what the goals of the project are. Ours are essentially the same. We're going to design, build, and demonstrate an ultra-high efficiency hybrid power system based on our pressure tolerant and high efficiency solid oxide fuel cell stack hybridized with the gas turbine. Talk a little bit about what we did in phase one. And in phase one of this project, our sole purpose or sole focus was on the actual solid oxide fuel cell stack, which we were designing specifically to the requirements of hybrid power systems. Obviously, these requirements include a relatively large stack size because we would be building 100 kilowatt systems, and you don't want to build a 100 kilowatt system with a lot of small stacks if you can avoid it. So we looked at things like a large cell active area for lower cost, improving sealing to enable stack pressurization, establishing internal reforming capability to maximize system efficiency. We started with one of our military stack designs with a 228 centimeter squared active area cell. And we established two stack design platforms, a full scale design, nominally 10 kilowatts, for use in the actual demonstration system that we would be subsequently building, and then a half-scale design for de-risking some of the design attributes of the stack technology. I have some examples shown of some of our stacks in the top right figures. The one on the top of those two figures shows both the 24 cell 228 centimeter active area stack, and then a short stack of our larger area platform. We were able to validate these stack performance at both the half-scale and full-scale design platforms shown by data in the upper right. We also developed a COM-cell model to predict optimum catalyst loading to balance thermal gradients from internal reforming within our cells. I don't have data on that, but that was also some pretty solid work we did in phase one. Also did a cost analysis. I think Rob mentioned the cost target for this program is at $1,800 per kilowatt. And we had to make sure that the stack we were developing was of an appropriate cost to meet that. So we did a cost analysis at a production rate of 500 megawatts per year. And from this analysis, we estimated cell costs of $77 a kilowatt and stack cost of $361 a kilowatt. We also completed a sensitivity analysis of the various costing assumptions. The area-specific power density is important because it determines the number of repeat units, and the repeat units are a significant component of the overall cost. So increasing power density is important without obviously sacrificing efficiency. Given that our cell design is electrolyte supported, the electrolyte material cost and membrane thickness are important drivers. The ferritic steel interconnect is also a key cost driver, and not just the interconnect, but there's a lot of other stainless steel components in the stack. So the cost of that steel is an important driver. You can't really ignore the cost of seals and interconnect coatings. There's multiple seals in each repeat unit, and interconnect coatings are going to be essential for long-term stack durability. And then finally, the cost of the stack conditioning process for curing seals and reducing anodes can be fairly significant, so we have to take that into consideration. So moving on to the phase 2 project, you know, we started work on this this past summer. We've been on phase 2 now for about a little less than a year. But our goal is to design, build, and demonstrate a high efficiency hybrid power system. Nexeris is leading this project. Our focus is on the stacks themselves. We're going to be building a lot of these stacks to support the demonstrations at C0. And so we had to do a little bit of scale up work so that we could meet the demands of the system builds. We're also collaborating with Dave Tucker at the National Energy Technology Laboratory on pressurized testing of full-scale stacks, leveraging a unique facility that NETL is currently building. C0 is leading the system design and modeling work, and also the controls development work. They've built a system model to inform specifications of balance of plant components, and then also to support the design of the control strategy. Brayton Energy is contributing their previous experience in SOC turbine hybrid system development, along with their gas turbine combustor and heat exchanger technologies. On the second year of the project will involve system construction, validation testing, and the project will culminate with an exciting demonstration of the hybrid system. That demonstration is planned for March of 2023, or February of 2023. You know, as we said, we're targeting the hybrid system at 100 kilowatt scale, 70% efficiency operating on natural gas. The system will operate at elevated pressure closer to maybe 2 to 3 to 4 atmospheres. I'm showing a simplified schematic of the system we're developing you know, as shown. The system's going to operate with the turbo machinery compressor supplying heated compressed air to the stack cathodes. It's pre-reformed natural gas being fed to the stack anodes. And unused fuel will be combusted with hot cathode exhaust and then expanded through the turbine to generate power. There's a lot of system design considerations that we're currently working through, and actually I should say we've worked through a lot of them, but a lot of different design decisions had to be made in order to get to the efficiency targets. The power split between the fuel cell and the gas turbine. We'd like to strike an appropriate balance between the higher efficiency fuel cell stack and the lower cost of the turbine. We're targeting nominally an 80-20 ratio of stack to turbine power. Stack thermal management is also a critical consideration given the large active cell area. As discussed earlier, we are pursuing internal reforming to achieve this. And details of the internal reforming and recycling strategies are extremely important to the success of the design. And we also need to consider how multiple stacks are going to be packaged into the system, balancing cost and complexity trade-offs between having one pressure vessel with multiple stacks or multiple pressure vessels with a fewer number of stacks. The system also needs to be designed with startup being considered, and obviously control strategies are critical to this system. In terms of market applications, We've done an analysis as part of our T2M activities on the project. There's obviously a lot of different applications across a diverse set of industries. Maritime, freight, passenger rail, and trucking industries would obviously benefit from the low emissions and high efficiencies of the system. Stationary power users, grid connected, standalone, can also benefit from improved resilience, sustainability, and energy independence. The system also can allow EV charging stations to be placed in locations with natural gas but limited power. Since we're targeting such high efficiency over existing or previous fuel cell turbine hybrids, there's obviously some serious advantages that we can exploit here. And we also can get even higher efficiencies with combined heat and power applications. So that's really the end of this presentation. Really want to thank ARPA-E for the support for the project. It's an exciting opportunity for Nexceris and our team. We also appreciate the technical and commercial guidance of our project monitors, Dave Tu, Rose Cox Galhotra, and Rakesh Radhakrishnan over the past 3 years. And I look forward to answering some questions.
Great. Well, thank you very much, Scott. It's very impressive how much progress you've made from a technology standpoint and growing Nexceris from nothing back in the 1990s. So that's congratulations. So I guess one question that I do have is that, I know our focus within Integrate is nominally natural gas fuel distributed generation, but certainly there's a lot of pressure on using any sort of hydrocarbon fuel and stationary power generation applications. And I wonder what that means for your kind of first nominal target for this ultra high efficiency, fuel-based energy conversion system. Do you expect the first product to be stationary, or are transportation applications potentially more attractive? I don't know the answer to that.
We're strongly leaning towards stationary at the present time. Yeah.
Oh, okay.
There's a lot of room in that space for a lot of different providers, and we also have companies like Bloom Energy and Fuel Cell Energy blazing a trail for us. Okay,
that's wonderful. And I certainly have a few other questions, but we are running behind, and maybe we can just address those in the group discussion. But the very nice presentation, Scott. It's very great. It was great. With that, I think we'll move to Michael Pastula from Fuel Cell Energy. And Michael, would you like me to share your slides?
Yeah, I think that's great, David.
Okay. PowerPoint. Share, whoops.
I think Rob and Scott have done a nice job introducing the Integrate project. Today I'm going to talk about the good work Fuel Cell Energy is doing, some of our business activities, and then also a few slides on the Integrate project. So great pleasure today to speak with you.
Okay, sorry, my DOE computer is a little bit slow.
Okay. So yeah, today I'm going to talk about high temperature fuel cell technology for the energy future. I'm Michael Pastula. I'm based in Calgary, Alberta, part of the solid oxide team at Fuel Cell Energy. So I think, David, if we just go to the next slide, we can look at what Fuel Cell Energy is doing and what are our business activities. So we've got a lot of activity in 4 key areas. In terms of distributed generation, that's our kind of historical business focus. We've had commercial molten carbonate fuel cells for more than 2 decades now, focusing on microgrid, shoring up grid reliability, combined heat and power. We're also getting into very different types of fuels, biogas in particular. In terms of some of the new focuses of the company, distributed hydrogen and producing hydrogen from biofuels. So one of our projects that we're working on right now with Toyota is transforming our carbonate technology to a trigeneration platform. So trigeneration means hydrogen, water, and electricity. And this is being installed right now at the Port of Long Beach. So this will be used to wash the Toyota vehicles as they come over from Japan, fuel them with hydrogen, and also power the port of Long Beach. If we go to the bottom left, we're leveraging our solid oxide technology for hydrogen energy storage and also pure electrolysis. And we can demonstrate close to 100% electrical efficiency on a lower heating value basis when waste heat is available to raise the reactant stream. So we can generate various types of hydrogen, green, blue, and gray from the existing grid. And one of the exciting things, as opposed to batteries, where energy storage is linked with the battery materials, in terms of RSOFC for energy storage, it's the costs are really linked with the hydrogen storage cost for medium to long-term storage. And in the bottom right, going there, carbon capture, we've got a significant joint development agreement with ExxonMobil to advance our carbonate technology for carbon capture, looking at integration with power plants for capturing carbon. And there's other industry opportunities there as well. So we have really one of the only technologies in the world that can produce additional power while capturing carbon. And David, if we go to the next slide, shows some of our examples of distributed generation. And really, we want to use this as a background and learning for the sub-megawatt solid oxide platform. So shown here are four examples of the molten carbonate technology implemented. In the top left is a 20 megawatt installation in Korea with KOSPO. So we're selling power to the grid and heat to the district heating system there. In the bottom left is one of the installations we're really proud of right now with Pfizer, 5.6 megawatt for improved grid reliability with their vaccine manufacturing. In the top right is a 14.9 megawatt system that's implemented in Bridgeport, Connecticut on a brownfield site. So targeting grid support and urban redevelopment. And this is an installation that's owned by FuelCell Energy. And in the bottom right is an installation integrating with renewables. So in this case, PV. So this is a 2.8 megawatt installation integrated with PV. So really we have more than 250 megawatts of carbonate fuel cell installed right now and around the world. Next slide, David. So in terms of technology platforms, we're a high temperature fuel cell company. In the middle, you can see the carbonate stack, and there's a picture of it there. The cell is approximately 2 feet by 4 feet. And in the background, you can see a 400 cell stack, and that produces on the order of 300 kilowatts of power. And we integrate 4 of these in a fuel cell module. And that's how these carbonate systems are really deployed, using large stacks for economies of scale at the megawatt level. The technology is well suited to operate on biogas and can also produce hydrogen through internal reforming, like the tri-generation system, or we've actually done some electrolysis work as well. So the technology has the ability to operate in that mode as well. So the solid oxide technology, the focus for the Integrate project, this is the technology I'm more familiar with. You can see a picture of our Csa Stack, what we call the compact solid oxide architecture stack. And I've got more details on that on the next slide, but it's a very compact, lightweight design. It's a formed true bipolar interconnect. And it's we feel like we've really minimized the weight in the technology, and we have automation involved in a lot of the manufacturing steps. Like the carbonate fuel cell, it can operate on a variety of fuels, natural gas, biogas, as well as hydrogen, pure hydrogen. And it can also do the internal reforming and electrolysis as well. And just putting the two modes of fuel cell and electrolysis together, you get the reversible solid oxide fuel cell, RSOFC. In terms of our solid oxide technology, we've also demonstrated it at a 200 kilowatt level. This is actually a picture. It looks like a rendering, but it's actually a picture of a 200 kilowatt system installed in Pittsburgh. And that was demonstrated in Pittsburgh, and it continues to run in Danbury, Connecticut today. Next slide, please. So the next slide shows our vision for the solid oxide platform, this compact Csa Stack. So you can see it's about 17 inches tall, 35 pounds, and there's 350 cells in that short height. So we've got a really tight, compact unit cell in the design. And this stack will produce about 7 kilowatts in power generation mode and can consume 36 kilowatts at 1 amp per square centimeter in electrolysis mode. And that equates to about 25 kilograms per day per stack. So we've demonstrated this technology so far in both power gen and electrolysis modes. And we're really leveraging that into 3 product spaces. So power gen, pure electrolysis for green hydrogen, and also RSOFC. And I've talked about the 200 kilowatt system, and we really see sub-megawatt and also a SOFC gas turbine hybrid being sub-megawatt product offerings for solid oxide. Also included on the slide are some conceptual views of a 4 ton per day, 7.3 megawatt pure electrolysis system, as well as a 1 megawatt, which is rated on the discharge power, 8 megawatt hour. And you can see the hydrogen storage there, as well as the water storage in the middle, and then the main converter and the power electronics there for the RSOFC. So we see multiple pathways for the Csa Stack, and there's actually some synergies, I think, in terms of pressurization as well. Hydrogen needs to be pressurized for storage, and so there's some synergies there developing a stack on the Integrate project for pressurized operation. We go to the next slide. Next slide has some details in terms of our process design. I think fairly similar to what Rob and Scott presented. So we have a kind of a direct coupled solid oxide fuel cell stack module with the microturbine. We're targeting operation around 4 bar pressure. So the natural gas comes in, it's heated, all the reforming takes place within the stack module, which is pressurized, and both the anode and cathode exhausts are combined and fed to a combustor for the microturbine. So yeah, going through the controls and dynamics is really important. We have project partners. They're not identified on the slide, and I apologize for that. University of California, Irvine, with Professor Jack Brower and team, and Brayton Energy as well, with Jim Kessley for the microturbine. So the microturbine power helps compress the incoming air, which is heated through thermal recuperation with the exhaust, and that's fed to the cathode inlet. So there's dual power outputs on this, both the generator on the turbine as well as the DC power from the fuel cell is converted to AC. And our power ratio between the two devices is around 85% solid oxide to 15% gas turbine. So in terms of markets for this, there's some data sponsored by the California Energy Commission. So focusing on California as a market, here's some market data. So looking at the less than half a megawatt and half a megawatt to 1 megawatt and high load factor, you can see that'll address about 21% of the targeted market. And in terms of that near-term market, that represents a $1.5 billion market, and that's just in California. So I think that complements some of the numbers from Scott and Rob earlier. And in terms of longer term, looking at megawatt and greater, there's a longer term $8 billion market, just looking at California. So we're targeting greater than 70% electrical efficiency, and that's what we've been producing in the models on natural gas. And looking at a really good turn down with such a system as well, so high efficiency to 50% load. And one of the things we've been looking at recently with transitions to even lower carbon fuels is hydrogen blending. And so far the models have shown up to 70% blending by volume with hydrogen, and maintaining good performance and operability with the system. Let's go next slide, David, please. Yeah, so we think this low cost, ultra high efficiency system really opens some doors, has some unique offerings. We are targeting a stationary distributed electrical generation market, and in particular microgrids, on-site power grid support. So really leveraging our carbonate experience, the megawatt experience in the sub-megawatt arena. And there's some examples shown below in terms of working with utility and gas companies in California, premium power places, things like data centers, hospitals. And as well, I mentioned earlier, SOFC is fuel flexible, like a carbonate. So digester gas, renewable natural gas has some good opportunities. Looking at Europe, more than 20,000 sites have been identified for biogas type applications. And there's also incentives in California for small farm waste management as well. So continuing to leverage that CEC study, there's some graphs and data in the on the right-hand side of this chart. So you can see just in California in the 50 to 250 kilowatt range, more than 20,000 systems. That's a 2 gigawatt market. And the types of applications you can see in the bottom part of the chart: office buildings, multi-family building, schools, universities, institutions. These are some of the prime locations for initial installations and initial product rollout. Next slide, please. So fuel cell energy, I guess if we just kind of step back and look at the overall energy landscape where fuel cell energy is working in, we're really working in 3 key areas: power generation, carbon capture, and hydrogen. And we're working both on the end user side, developing products and demonstration platforms for end users. But we're also looking at the generation side. And on the generation side, there's a large need. And some of those are identified, how we can help different industries, such as existing fossil fuel power plants, nuclear power plants, and also renewables. So I think just with that, I've got one more slide, just closing. I want to thank you for your attention today, and I wanted to close with fuel cell energy's mission to enable the world to live a life empowered by clean energy. Thank you.
That was great. Thank you very much, Michael. It was a great presentation. I just got to get out of slide share modes, or at least a presentation mode, so I can see the questions. But while I'm trying to find them, I do have one. So you identified 3 future businesses for fuel cell energy: hydrogen generation, carbon capture, and power generation. And I know historically power generation has been the market. Do you see power generation as being fuel cell? I mean, if you can't talk about this, that's fine. Do you see power generation as being fuel cell energy's primary market, 10 or 20 years from now? Or do you see the others as being more important to fuel cell energy? One of the others.
Yeah, that's a tough question, David. I
It
think
is,
there's
yes.
a lot of excitement with hydrogen right now. That's something we're definitely sensing. I think just leveraging the history of the company, power generation is more what fuel cell energy knows and what we've deployed in the system. So it's going to be really interesting how the hydrogen arena develops. And for me, one of the aspects is really the implementation in the field. So the megawatts or gigawatts that's implemented, there's a lot of really aggressive goals around the world in terms of net zero and 2050 being it's a long-term target, but it's a near-term target in a way in terms of the amount of change that has to happen. So we're going as fast as we can internally. And one of the things we're doing this year and going into next year is a 250 kilowatt electrolyzer system that we're going to demonstrate at INL. So that's one of the kind of flagship electrolyzer projects that we're working on right now. But it'll just be kind of speed to market. I think it's a bit of a race to see how these technologies can be deployed in green hydrogen production and also energy storage.
Okay, well that's great, Michael. And I've got a few more questions, but we should probably move to our last presentation. Then hopefully we can have a discussion amongst all the speakers and anybody else that has questions or comments to make. And with that, thank you very much, Michael. That was great. We should probably move on to Stefano. Stefano, are you there?
Hello, can you hear me?
Yes, we can.
Hello, good afternoon, everybody. First of all, I can show myself. Unfortunately, my bandwidth is not very stable, so maybe during my presentation, I will stop my video.
Okay.
If it's not a problem, just to share my screen, but I present myself, first of all.
Great. Well, nice to see you.
Good afternoon, everybody. First of all, thanks again for inviting me today to this workshop. My name is Stefano Barberis. I am a former PhD student in University of Genova, and now I am a project manager from RINA Consulting, and I'm here today to present you the outcomes of a European funded project named Everywhere, whose goal is to realize and test and demonstrate in real environment the use of PEM fuel cell as heart, let's say, as core of a transportable genset. I hope you can see my screen. I'm now going to maybe stop my video just to guarantee a good band. Okay. Okay, so
we can see
can
your
you
screen.
See my screen? Can you see my screen, David?
Yes, we can. It's not a presentation mode just yet, but we can see it.
Okay, yes, for sure. Okay, so a few words from my institution. First of all, I am, as I said, I am a project manager from RINA. RINA is the largest Italian engineering company. Actually, we are a 160 years old company that formerly was only, let's say, a naval register and a classification society, and now is becoming one of the largest European engineering firm. Personally, I am from the energy division, which is a division working in projects all around the world. In this moment, strongly focused on energy transition, of course, but with a strong experience and expertise in the oil and gas sector. Starting from this experience of the oil and gas sector, we are exactly now transferring know-how to hydrogen. Some hiccup, okay. We are transferring know-how to hydrogen and trying to promote the use of hydrogen in all our business units, in the marine sector, in the infrastructure, energy and mobility, industry, inspection and field, and certification, which is the other, together with the Naval Classification Society, the other historical business of RINA. Generally speaking, our company is super focused in R&D with a strong experience in European funded project. Actually, we have been in the recent Horizon 2020 framework program, the second most present industrial partner, with more than 180 participation in Horizon 2020 projects. Currently, we are working in around 100 Horizon 20 projects, coordinating among around the 20% of them. Among them is also Everywhere, which is a project that we the framework of Horizon, the framework of which is, as you
Stefano,
know, a private and public partnership.
Stefano?
Yes? Yes, please.
You may want to turn off your video. The audio is a little bit garbled.
Yes. Sorry, just 1 second.
That's okay. No. We very much appreciate your presentation.
So I'm just saying that some projects are funded by the FCHJU, which is the private and public partnership, the European private and public partnership, promote and demonstration projects in hydrogen and fuel cell technologies. This FCHJU is now in national the new that European Commission really kicked off. Generally speaking, as I said, we are coordinating several projects. One of them is Everywhere, whose goal, as I said, is to demonstrate the use of fuel cell in transportable power gensets. What it means, instead of the use of traditional diesel engine, the idea is to replace diesel engines with PEM fuel cell, fueled, of course, by hydrogen, by pure hydrogen. The goal of the project is to realize 7 gensets, 4 25 kilowatt and 3 100 kilowatt, to be tested around Europe in cities, construction sites, music festivals, temporary events. And the goal of the project is really demonstrative. So the goal of the project is to showcase to, let's say, European citizens as a whole, but the European industry and society as a whole, the fact that hydrogen can operate safely in cities in really daily applications such as the temporary power gensets. So our objectives is related not only as our objectives are related not only to realize these transportable gensets, but also to study how to launch them on the market, studying, for example, all the aspects related to regulation, all the aspects related to safety and permitting, so to facilitate the future marketability of our genset, but also studying how to logistically, distribute such genset, but particularly how to logistically refuel our storage bank. And this is a very ambitious project because at the end of the day, we are working as an orchestra of partners, because we are talking about a collaborative project with partners from all over Europe to realize a single product, which is at the end of the day first of its kind, because when the project was kicked off in 2018, at the end of the day there were no alternatives. Now in this moment we know that there are some competitors of our Everywhere genset, but at the end of the day, really, when we started the design of this system, we really faced the fact that we were realizing a first of its kind project. So, and we were realizing a first of its kind product, bringing it directly to demonstration. So, in a real pre-industrial project. We also understood from our stakeholders, from our potential customers, that it's very important to think about how to launch on the market such genset, how to refuel them with a great importance that the stakeholders, particularly looking at, for example, music festival, a great importance that the stakeholders give to the origin hydrogen. So, for example, we always receive request of usage of our genset. Second question is the hydrogen green? So at the end of the day, we are working with customers that are keen to have a real 100% sustainable solution for their events, for example. As I said, the project is a collaborative European funded project, very driven by a project driven by an industrial frame, plethora of partners, with, for example, PowerCell from Sweden providing the fuel cell subsystem, Linde from Italy providing the hydrogen management, Genport and Friem from Italy as well providing the and control, the master control unit of the system and the power converters, MyTech providing the hydrogen storage, Acciona, that is one of the largest European construction society, providing one of our demo in their construction site, etc. So a very industry-driven consortium that is strongly committed to realize such genset. But the first question is why hydrogen genset could be, let's say, competitive. Well, for sure, the first thing is that we are targeting a market that is very keen to sustainability, as I said, with a lot of attention to reduction of emission, particularly if we look at construction sites and events industry. And currently, you know, this is a market, the market of temporary genset is mostly 99% served by internal combustion engines that are 90% fueled by diesel or by natural gas. The other competitor, of course, of an hydrogen fueled genset is our battery. But of course, the battery system has, you know, a drawback related to the potential working in extended run time, particularly for the energy capacity. So generally speaking, you know, what we are promoting via our Everywhere project is the fact that PEM fuel cell systems could have a lot of, you know, a lot of point of strength, looking at zero emissions that they are proposing, of course, zero noise, but of course also the fact that if compared to battery, they can work thanks to a large and proper sizing of the hydrogen storage for an extended, a quite extended runtime, working also in different ambient conditions, so even with high temperature, dusty air, etc., with a proper air filtering for the air inlet to the PEM fuel cell system. As I said, we are realizing two sizes of genset, one 25 kilowatt and one 100 kilowatt. In the whole project, we will realize 425 and 100 kilowatt system. And this system that is a containerized solution will travel together with a pressurized hydrogen storage with a hydrogen tanks at 350 bar. Actually, our bottles are able to operate and work at higher pressure because we work with MyTech bottles. We can work with MyTech bottles up to 525. But in this moment, we are studying and we are demonstrating the use with 350 bar because 350 bar in Europe is the maximum pressure that hydrogen can be, let's say, disposed at a hydrogen refueling station. In that sense, we thought to realize a so-called two boxes solution. One box, which is the container for the real fuel cell power subsystem, so the real genset, let's say the engine, let's call it, and another box that is the pressurized hydrogen storage tank. We started to, design our system, obviously looking at safety most of all, and separating, for example, the different environment of the genset. So we defined three different environments, three different spaces and volumes inside the genset, one dedicated to the fuel cell subsystem, one dedicated to the thermal management of the subsystem itself, and one dedicated to the power conversion unit. Also to, with a strong separation among the first and the third volumes and spaces, also to guarantee the proper safety and avoiding any potential risk of ignition from the hydrogen. In that sense, also working with a containerized solution, this facilitated transportability of our genset. And we also targeted, for what it concerns power conversion unit, the possibility to realize a human-machine interface in terms of both controllability and plugs where the loads could be connected, that are identical to the traditional diesel genset, in order to guarantee an easiness of use to the end users, or let's say something that is really, really similar to diesel genset, where people turn the key and the power is on, let's say. So starting from that designs and renders, we realized the first two prototypes that you can see in these pictures. The idea of having these three volumes also enable us to properly enter inside the different volumes to for operation and maintenance, to guarantee a proper control of everything from hardware and software point of view. And I really would like to invite all of you to take a look to our website, www.everywhere.eu, where there is a video tour of our genset, so you can easily understand how our genset works and, let's say, a better detail of this distinction of the three volumes. We, as I said, now realized two prototypes, one 25 kilowatt and one 100 kilowatt, coupled with hydrogen storage bundle, a hydrogen storage bundle that is able to operate, enable the operation of the genset for at least 8 hours full power. So we are working for the 25 kilowatt with a 3 bottles bundle that you can see on the right, and for the 100 kilowatt with a 100 bottles bundle. The first one is 13 kilograms. The second one is 41 kilograms. And they can operability of our genset for 8 hours full time. The good things of this bundle is that, if you would like to work with larger capacity, it's very simple to enlarge the hydrogen storage capacity, not only connecting to our genset more than one of our bundles, but even connecting commercial bundles that will be, let's say, controlled by the hydrogen panel system that is equipped, that is integrated directly in the bundle, as you can see in the picture. So let's say now we are approaching the demonstration campaign, which is crucial in everywhere. Unfortunately, in 2020 and 2021, due to pandemic, we couldn't start such a campaign, mostly because many of the events and festivals that we engaged for the project were cancelled. But we are going now to start for 2022. We are confident to do so. We are also going to have a first demonstration in, as I said, Acciona construction site. But in this moment, we are looking for potential new demonstration, new opportunities. So we are really starting now to engage new partners for new solutions, let's say. So this is, as I said, a European funded project. So demonstration is crucial also to showcase that this system can be on the market. Also because, as I said, we are already receiving a lot of requests of interest. So the funny thing of this project is that when we started the project, of course, we thought about the fact that in few years we would have received many requests of interest, but we really didn't realize that such requests of interest would have come during the project itself. So we are already, let's say, trying to push a little bit more and going a little bit faster, but the project will end in 2023, achieving TRL 8 thanks to its forward demonstration campaign. But the idea is then to launch them on the market, maybe also upscaling the scale, because we understood that, for example, we understood from our stakeholder group that for example, 25 kilowatt is a very, very small power capacity size, while 100 is really the minimum for our type of customers that, just for information, are not only in construction sites or music festival or events, but we also, for example, receive the expression of interest from the movie sets that are always trying to find zero emission and zero noise, particularly when they operate during the night in cities, to guarantee a larger sustainability and a larger operability of their movie set. So just to finalize, I really invite all of you to get in touch with us, take a look to our project website. If you would like to know something more, please do not hesitate to contact us via the website or via my email. And of course, if you are in Europe and you would like to host a demonstration, get in contact with us, because there could be the chance to host one of our everywhere genset. Thank you a lot again for the invitation, and I hope that this new product could be of your interest.
That was great, Stefano. And I actually do have one question, but I have a question for our Nettle host. But actually, before that, from a logistics perspective, we're at the limit. Do we have a few additional minutes that we can have a discussion?
Sure. Because we have a half-hour break that we can cut into, so it's not a problem.
Well, so one question, Stefano. I mean, I really like this idea. It's neat. I can imagine working next to a PEM fuel cell sounds much more attractive than working next to a diesel generator, for example, at a construction site. But even from a logistics standpoint, do you have a sense of how frequently the diesel gensets have to be refueled themselves? Is it every 8 hours, like you have to do with your hydrogen-based system?
Okay, so let's say I have to admit, frankly, that the current size of the hydrogen bundle, as I said, the full power production for 8 hours is mostly due to the budget of the project. So if we would have had higher budget, probably the bundles would have been larger. Nevertheless, generally speaking, consider that, for example, for temporary events or for festival, the refueling of diesel happens each 2 days, normally 2-3 days. Of course, they have a limit related mostly to safety, because fire department, who in Europe gives the formal okay to operate a diesel genset and also our hydrogen genset, cannot accept a huge amount of diesel or of oil or gas in a crowded area such a festival could be. So normally, let's say that maximum 24 hours full power is the traditional sizing of the storage. So in our case, if we had let's say a limited budget, probably we would have sized the storage in such a way.
Okay, that's great. So you mentioned noise. So is noise an attractive feature for people that are running festivals and things like that, compared to the diesel gensets? The fact that your system has no noise, in addition to the fact that it's hydrogen fueled and clean.
For the festival, it's more actually the goal is, festival are very natural friendly, green looking, let's say. So they are trying to reduce their emission, generally speaking. So for festival is more a matter of reducing the emission. While for movie sets, for example, is more on the noise emission, because as you maybe know, particularly for urban movie sets, they are used to have the run during the night with a lot of lights emulating the daylight. But if they are in the middle of the city, they cannot use, for example, diesel, because they produce a lot of noise during the night. So they are looking at something different in this way as well.
Okay, that's great. And so now we can maybe move to the general panel discussion. And we do have actually one question already. Harsh, would you like to unmute yourself and ask it, or would you like me to?
I can ask the question.
Okay.
We have very interesting technology development going on, and there have been many programs from the Department of Energy and others on hydrogen. So I'm curious about where we are when it comes to actual commercialization, right? So the critical things there is cost competitiveness and ruggedness reliability, and of course, there is an understanding that there are features, especially when it comes to things like sustainability, that these technologies offer. But where do we stand now compared to existing solutions? And 5 to 8 years in the future, what applications do you see with most potential? This is a question to all the panelists. Yeah, thanks.
What we saw is that particularly if we look at short-term rental, so rental of genset for less than 1 week, in this type of contracts of rental, the weight of the capex in the cost that at the end user is spending is only the 20%, because at the end of the day, for short-term rental, the highest percentage of cost is related to shipping, to fuel, to transportation, etc., etc. So at the end of the day, if we target particularly short-term rental, it can be cost competitive. Consider that in this moment, festivals are used to pay rental for diesel genset with a price that can achieve up to €1 per kilowatt hour. Okay, so this is something quite high, and it is something that is manageable even by hydrogen or fuel cell, which, as you mentioned, are obviously more expensive from a capex point of view.
And I guess I could just say from an overall goal perspective for the Integrate and Reach programs, we did the best we possibly could with the information that we have to set efficiency and cost targets that we thought were consistent with the commercial success of those systems for both stationary distributed generation applications as well as the aircraft applications. You can debate whether or not we did a good job, but those metrics were intended to enable those systems to be very attractive from a value proposition standpoint. I don't know if our Scott, Rob, or Michael, do you guys have any thoughts?
I guess I can jump in and just say a few things. Maybe it's too obvious, but I think in terms of where the Integrate project is right now, we're at the prototype stage, the early demonstration. So we need to tackle cost from a few different points of view. So we feel like we have a very good stack cost story and what we've demonstrated so far in terms of pilot manufacturing. We need to get the initial system at the appropriate point on the cost curve. So the first system is not going to cost $1,800 a kilowatt installed, but we need to have the path to the low cost point. So really at the early stages, at the demonstration stages, really having a concept, a low cost concept. I think Stefano's presentation was interesting, kind of bringing some of the niche characteristics that people look for, the noise, that's really important to some people, emissions. There's different thoughts on CO2 and taxing of CO2. These early systems too, really high temperature systems, they don't start up in 5 minutes. So we want to look at systems where there's a high load factor and really kind of switch the paradigm where the power system, the SOFC system is the primary and maybe the grid is the backup. And the combination of those two give you the kind of the ultra high reliability that people are expecting and looking for. So those are just maybe a few comments on it.
That's great. And so I think I heard in actually all three of the Integrate presentations that, there may be these opportunities in the transportation markets for aviation and maritime applications, but the focus of the Integrate program was on stationary applications, and it seems like the teams still believe that stationary distributed generation applications are is the right market entry for the technology. Would any Scott or Rob or Michael, would you guys disagree with that statement? Or
I certainly can't disagree with that statement.
Okay.
I think the technology needs to be proven and the technology needs to be demonstrated and lifetimes achieved, all of those things, and starting out trying to get to the required levels of durability for transportation applications as an entry point would be a challenge.
Yeah,
and certainly
what seems interesting in some of the analyses we're doing is previously fuel cell systems for stationary would have challenges in places that weren't California or Manhattan in the US where you have high spark spreads. With these targets, we're seeing places like Boston and Denver, other urban areas begin to open up competitively against other prime mover technologies, at least, including the grid and including renewable installations. In fact, there are no renewable PV battery systems which compete on a pure life cycle savings viewpoint in the analysis we've done. So it's just using today's PV prices and of course future fuel cell prices, which isn't apples to apples, but as Bloom is showing, the future is getting closer because their costs are coming down now pretty well.
So maybe one question that I have is I've been advertising, right or wrong, that these hybrid systems and solid oxide fuel cell systems are fuel flexible, and I think they certainly are from an ideal standpoint. You can design them to operate on probably any fuel you would like to. Certainly low sulfur is attractive. My question, what I think practical question is how fuel flexible do you think the systems that you're designing are? How many what hardware changes or control changes would be required to move from natural gas to ethanol to synthetic aviation fuel to hydrogen, for example? Or are changes required? Or is it too early to tell?
I guess I would suggest that there are paths to get to fuel flexibility, but when you're starting out with natural gas and going with internal reforming, you certainly have to change the internal reforming to external reforming. That's going to have an impact on the thermals in the stacks for certain. And so, there are obviously paths that people have identified to address the thermals, increasing airstrikes and things like that. So I think it's all ultimately doable. I mean, it's not a complete redo, but there certainly would be some component and operational changes.
I think it's probably like any other technology. You don't buy a stationary engine that fires both natural gas and diesel very easily. You've got to buy the accessories or this, you cite it for the fuel. I think that's probably easily done with these systems. I guess there will be questions though whether the economics stay the same. So with hydrogen, of course, the fuel cell would like internal reforming in solid oxide, right, to lower the airflow requirements. But if you go pure hydrogen, then you're going to need more airflow.
And I know, Michael, you had a 70%, I think, hydrogen to natural gas upper limit. Was that driven by thermal considerations? You're on mute, Michael. You're on mute, Michael. Sorry.
Sorry, no, it's more to do with our integrated system being a hybrid system and the gas turbine being truly coupled in terms of reactants and pressures with the gas turbine. So comparing a hybrid system to a base solid oxide, it's it's more integrated, and the operability is more integrated. So the operating window is much more rigid. So with kind of a lower performance base solid oxide system, you don't have as many constraints. So for instance, the airflow and the linkage of airflows and gas turbine operation and pressure, there's a lot more coupling there. I just want to add one thing though, like in terms of our solid oxide direction, we've actually kind of gone to a smaller stack platform area-wise. So we actually had I think one of the largest solid oxide platforms in the world, a 550 square centimeter active area cell, and we've decided to go to a smaller active area, 81 square centimeter. And fuel flexibility was one of the reasons for that. So having the smaller area and having more flexibility in the stack thermal management was really important. So for our SOC, for instance, you want to operate on pure hydrogen and do that at high performance and efficiency. So with variable internal reforming and airflows and stack operation, we're finding the smaller area platform that's well suited for automation is a good technical direction.
Okay, great. Thanks, Michael. And Ben, thank you for turning on your video. I see your hand now.
Yes, I wanted to ask, since we've got expertise in different types of fuel cells here, particularly for larger scale commercialization, are there any critical material constraints that are a concern for scale up with the different technologies?
I mean, we haven't seen any. at this juncture. Most of the solid oxide is, it's nickel, it's zirconia. These are nickel's usually the most expensive raw material in the stacks, and there's plenty of that.
About the cathode materials, or I guess scandia is present in some stacks.
Scandium,
Maybe
yeah,
more.
there's perhaps some concern with the scandium supply, although there's quite a bit of it in, I believe, in Australia. But Russia controls a lot of the scandium supply, as I believe China does. So yeah, that I think if you're going to go the route with scandium stabilized zirconia, which a lot of electrolyte supported platforms do, that could be a concern going forward.
I think there's some
Okay.
short-term constraints just with the pandemic affecting supply chain. That's something that's being wrestled with in the near term. But in terms of the longer term, yeah, I don't think there's any kind of fundamental materials. It's more, I think, like you were saying earlier, Scott, basically demonstrating the lifetime at the operating condition in the field. That's really the key thing. And Fuel Cell Energy has gone through a 5-year stack into a 7-year stack with our carbonate technology. So we want to follow the same type of model with our solid oxide platform, but it's more the integration of all those materials working in the stack. That's the challenge, and kind of extending the life of the stack.
Okay.
Are PEM fuel cells still critically dependent on platinum as part of the system?
Stefano, you're probably the best position to answer that.
Sorry, I didn't get the question. Sorry for this.
Go ahead, Ben.
Do PEM fuel cells still need platinum to operate?
Yes, of course. Consider in any case that from our side, we are relying on fuel cell coming from the former automotive R&D, because at the end of the day, PowerCell Sweden is a Volvo spin-off. So in our case, looking at our project, we are targeting to use, how can I say, as much as possible reliable solution. Okay, so of course, to decrease the cost, as you said, we should act maybe on reducing the cost of the electrodes, like platinum, etc. But also, for example, reducing the cost of the membrane. But generally speaking, for us, the goal is more reliability. So even if it will be more expensive, also considering what I mentioned earlier, that particularly for short-term rental market, the capex is not so affecting the product cost. No problem in our head, let's say, to commercialize a system that could have a higher capex but guarantee more reliability and security of supply at the end of the day, because this is what you have to provide for temporary power.
Thank you.
Great. Any final questions or comments? Anybody or Dave?
No, but if we don't hear anything, okay, wait a second.
Dimitris, do you want to make your point?
Yeah, hi. Thanks for giving me a chance to
Yep,
speak
that's good.
at this panel in the comment session.
Thank you. Yep.
Just from the internal combustion engine perspective, so I know there was some discussion mentioned about the flexibility, right, and how we have to design the engine for certain fuel systems. Now, usually, of course, there's the obvious cost aspect, but there are advanced combustion modes such as the dual fuel combustion or reactivity controlled compression ignition that I think can offer quite a bit of flexibility. So using the anode off gas to essentially fumigate in the manifold, right, and then direct injection of diesel can provide a higher net fuel conversion efficiency we saw than just traditionally trying to burn the anode off gas with a spark ignition source. And then if you consider the flexibility, if you have a fumigated manifold with the anode off gas, you could sub that out for essentially either natural gas or natural gas hydrogen blends. And the diesel can either become more traditional biodiesel or perhaps some of these naphthenic bioblend stocks that we're working on the Co-Optima project that are CFP derived with hydrotreating. And then imagine you can even sub the engine to run 100% either on, let's say, natural gas or natural gas hydrogen blends with no diesel fuel, or the other way around to introduce just diesel fuel. And again, it would be a compromise, but as a balance of plant, introducing that flexibility on the engine side for some of the intermittent operation could give us that flexibility that we need for the load following and the fuel availability that exists.
No, I think that's a great point you're making, and Sage Kochjan did some similar work on that as part of the Integrate program in terms of reactivity controlled engines using natural gas. I think there was still some requirement to knock water out of the anode exhaust, but the use of just a tiny bit of natural gas was a very valuable control lever to use in the recip engine. But I think that's a great point.
Yeah, and then just one follow-up question on that water. Are there any strategies that you've identified as clear winners on how to essentially remove the water from the anode off gas that you see as kind of winners moving forward?
Unfortunately, Rob dropped off. Just condensers is all I recall at a high level, but I've actually never seen them. But that's really the only strategy that I'm aware of that has been employed. I think that's what Sage used as well.
Wonderful, thank you.
Okay, great. Well, thank you all very much. Go ahead, Dave.
No, I was just going to say the same thing, Dave.
Okay. Well, thank you all very much. This has been a great discussion, and thank you very much to our panelists and speakers for taking the time to share your thoughts. It's been very valuable. It was very nice meeting you for the first time, Stefano, and I look forward to talking to everybody again soon. Well, thank you all very much.
And so I'll just follow up saying the next session starts in about 8 minutes, and because of that, I think we're going to skip the breakout sessions, Brian, and we'll just give everybody a chance to get up and stretch and use the facilities, get a cup of coffee, that kind of stuff. So we'll see you back in 8 minutes. Also, again, at the end of the day here, the last session will be open discussions. So please, if you have questions you didn't get a chance to ask, I encourage you, to bring those to the last session of the day. Thanks very much, and we'll see you in about 7 minutes.
Great. Thank you.
Thank you.
Good rest of the day.
Thank you, and thanks, Dave, for chairing this session. It was really great.
I apologize for my poor time management, but great discussion. Nice job, speakers.
I think that you're not alone. Okay.
Okay.
All right. Thank you.
Thank you, David. Thank you, David. Bye-bye.
Hi, Brian. This is Paula.
Hi, Paula. How are you?
Good. So I think this presentation will be the second presentation. So
Yeah, I just wanted to make sure it worked the same way in a meeting as it does for our events, because they're a slightly different platform. And I wanted to see how long it would take to upload the file. So I was just testing.
You can see the slides. I can see the slides that you're sharing now.
Yeah, or you guys are going to use two different presentations, right? Or are you both working off the same one?
What do you mean 2 different presentations?
Are you sharing a presentation, or is he doing this by himself?
I just have a slide to introduce the session, and then the other speakers will share their slides.
Very good. Yeah, I'll bring this up when Steve is ready to do his presentation.
Right, thank you very much.
Mm-hmm.
Morning, Paulo.
Morning, Fernando. How are you?
Good. You want to test the connection?
Sure. Yes.
Might as well. Never know, Ray. Let's see here. You see the PowerPoint?
I think it's loading because we see a blank slide.
Okay.
Yeah, it may take a second or two. There, we see your presentation now.
Okay, let me try to put the full screen here.
It's still
some lag there, right? Okay, and then I need to probably switch the display setting, right? Swap.
No, it's showing us your full presentation screen, so you're good.
Oh, it is. Okay, that's a miracle.
Doesn't happen for everyone, so yep, it's great.
Ready, so I can stop here. I don't know if somebody else wants to test as well.
Hi, Paulo. Luca here. I can make a test too.
Yeah, please go ahead.
So let's see. Share. Okay, so can you see it?
Yes, looks good. Just put it into regular presentation mode and it's full screen. Perfect.
Okay, great.
Okay.
Yeah, hi, this is Tyrone's. Maybe I'll do a test here.
Yes, please go ahead.
Okay, you're on a Mac, so we're only seeing a portion of the screen. I don't know if you can zoom to it. There you go.
Is that the whole thing? All right.
Yep, you're in good shape.
All right, good.
And then Isaac, I think you want to test if you want to test your slides, you can do it. Isaac, we saw you for a few seconds.
This is Isaac Frampton. Is mine working?
The microphone is working. If you can try to share your slides.
Yeah, you were unmuted a second ago, Isaac, but now you're muted again. And there, we're starting to see your presentation now.
Yes. Yeah.
And it's just a portion of the screen. If you can.
All right, so that does work okay?
It does if you can put it in presenter mode and then or presentation
No, I
mode.
moved to noon.
Whoop, that
There you
probably
go.
isn't what you wanted. Does that still work okay?
That'll work perfectly.
Right now, but yeah.
All right, good.
Yeah.
Now if I can figure out how to stop sharing.
There we go. There you go. Perfect.
Okay, now I try to share my slide. Okay. Do you see my slide?
Yes, we can.
Okay.
All right, you're full screen now.
Right. Yeah.
Your audio has become quite quiet. I'm not sure if you moved further away from your.
Okay, now is it
That's
better?
much better. Yeah.
Okay.
So Paulo, before we get started, can we go ahead and have Nana go through the rules
Yes.
real quick?
Sorry, yeah. Okay.
So Nana, can you go ahead and go through your slides real quick?
Yes. Let me share it. Can you see my screen?
We can.
Yeah.
Okay, good morning, good afternoon, and good evening, all the participants. And I need to go through this. With all of you. This workshop is considered as open to the public event, which means all the information included in your presentation and talks and discussion need to be publicly available before this meeting. So make sure that your presentation and your discussion has been reported in some other like conference or report or paper, or if you have sent me your slide before, and I think you're good to go because we posted all the slides on the NTL's conference page. So that's good. And another thing is the entire workshop will be recorded because we're going to develop a technical note after the workshop, which will be available to all the LEAP participants when it's available. I'm going to send to everyone when it's ready. And also the recorded video will be posted online, I think maybe in YouTube, and I will send out the links when it's available. And we suggest you to turn on your camera when you are presenting or asking questions, but if your internet is not good enough, your camera might affect your audio, then you can turn it off. Since we have working from home for a really long time, we wanted to talk to people instead of talking to the computer anymore. And also since we have many people online at the same time, so please make sure that you mute yourself except when you're talking or presenting or asking questions. And if you have any questions during the presentation, feel free to post them in chat or just unmute yourself after the presentation and ask your questions. That's all. Thank you very much. Paula, you can take it away.
Well, okay, so first I'm gonna go ahead and introduce Dr. Paula Pazzini, who is who's a research engineer at Ames Laboratory, and who's been focused on controls development for hybrid systems now for at least a decade.
Yeah.
Sorry, Paula, I didn't want to give away your age, but so he's been involved in this field for quite some time. So thank you, Paula, for hosting this session, and I'll let you go ahead and get started.
Thank you, Dave, for introducing me. Welcome everybody to the session of control development for energy systems, session 8 of the LEAP workshop. This session will discuss the development of control strategy for novel power cycles and existing state-of-the-art adopted in industry for existing power systems. We have six speakers, 3 from industry and 3 from academia, that will provide an interesting perspective on the development and validation of controls. We start with a speaker from West Virginia University, then from Electric Power Research Institute, EPRI. We continue with University of Genoa and Colorado School of Mine, and then with C0 and Kohler Engine. Each presentation will take approximately 7-10 minutes, followed by a 5-minute question. I'll try to take 1 or 2 questions after each presentation. If you're short in time, we can have a panel discussion at the end. And if you have any question, please write your question in the chat, or I can read the question for you, or you can, like Nana said, you can unmute yourself and ask the question. Okay, saying that, let me introduce the first speaker. Let me stop sharing. Why is it loud? Okay, So the first presenter is Professor Fernando Lima. Fernando is an associate professor in the Chemical Engineering Department from West Virginia University. His current research focuses on modeling, optimization, and control of advanced energy and power systems. His research awards include the American Chemical Society Petroleum Research Fund, Doctoral New Investigator Award, the Faculty Early Career Development Program Award from NSF, and the West Virginia University Statler College of Engineering Excellence in Research Award. Professor Lima is a program director, is a program coordinator for the system and process control, and is also a member of the editorial board of Journal of Process Control. So Fernando, whenever you're ready, please go ahead and start your talk.
Thank you, Paulo. I found the button here. Can you see the full screen?
Yes.
Okay, great. Okay, perfect. You never know. Okay, good morning, good afternoon, good evening, everyone, wherever you are. As Paulo said, I'm Professor Fernando Lima from West Virginia University. So today I'm here to talk about model predictive control power plant cycle. So power plant cycling, even though we are focusing here on coal and natural gas fired power plants, of course, these approaches that we developed are relevant and can be used as well to hybrid systems, and I'll touch on that as well. So I think many of you have already seen the motivation for this problem here in this LEAP workshop, so I don't have to extend myself into this here. But the overall idea is that the coal and natural gas fired power plants may need to cycle their load due to the presence of renewables, in this case, wind or solar. And of course, if we have to do this power plant cycling, it kind of defeats the purpose of having renewables, because the power plants will be fluctuating around their design point, and then of course more emissions will happen, and this will have other impacts as well that I will discuss. So the consequences are, so we may have to increase the cost and maintenance of cycling plants due to stresses, cold or warm startups, and also, as I said, decreasing the efficiency as we're operating away from the design base load point, and increasing emissions, which is critical because, as I said, they kind of defeat the purpose of having renewable energy integrated into the grid if you're going to be increasing the emissions, right, of the power plant. So our approach is to develop process models for power plants and assess the cycling in terms of developing algorithms for real-time optimization and model predictive control. So I'll be discussing here the focus of this talk because of the time of discussing only the Mpc effort. So what is model predictive control? I think that we have a couple of other presentations coming up on this here. And the main motivation for using this type of controller, which is an advanced control, is the challenge of handling constraints with traditional feedback control strategies such as PIDs. And also some decoupling that we may need to do using other strategies, such as if you have multiple input or multiple output systems. So the idea here is to use what we call this receding horizon or predictive controller, and I'm going to walk you through this in 1 minute. So the idea is if you have a set point trajectory target here, if you can see my pointer, and you have a Y or an output trajectory, you would like to get to that set point as quickly as possible, right? And of course, in cycling, it will be a bit more difficult. The controller will actually calculate the input or U moves, the optimal moves here within this control horizon M, so that you get to the set point as quickly as possible. And this is receding horizon. So what happens is the first control move is implemented into the plant, the calculation is rerun, and then another prediction is made, another calculation is done in terms of solving for this optimal input profile, and then implemented into the plant again. Some advantages of this, of course, you can handle constraints and you can handle more complex systems. We have developed several types of Mpc algorithms, linear Mpc, nonlinear Mpc, which is preferred. However, the issue is, of course, when you go with more complexity, the computational time becomes a challenge. So here are some of the algorithms we have developed. I'm not going to talk about all of this in detail, so don't worry about it. We have the references here. This is, I believe, all will be shared with you. So, but the main person who worked on this is Hashin, our a PhD student who's now at the postdoc at the National University of Singapore. So his thesis is pretty comprehensive and involves all of these papers and many of these control methods. So we have developed the traditional one used in oil processes, the dynamic matrix control, DMC, which is linear based on step responses. We have developed different nonlinear MPCs, one based on sequential quadratic programming solver, the other one based on interior point method solvers, the so-called IP-opt, that's from Professor Bigler's group. And we also used one of our own in-house solver, what we call the modified SQP, which inspired Rasheen in our group to develop an MPC toolbox in MATLAB, which has been shared with DOE as well, that funded this project. I'll talk about that as well. And the main advantage of that is that there's some tricks there in the optimization to make the solver faster, with faster conversions. And that was kind of the idea of this particular problem or solver. So I'll talk about a couple of applications here. The first one is a supercritical pulverized coal-fired power plant. And the model has been developed in Aspen Dynamics. And this is a collaborative effort as well with Professor Turton, and who retired, and Professor Bhattacharya, who's at WVU. So we developed models for boiler, heat recovery system, turbines, and also for carbon capture subsystem using the MEA or the amines for absorption process. And this is about 600 megawatt plant, and it's based on the baseline report from NETL. So going straight to the results here, we develop all of those MPCs, and I would like to show to you here the performance. So here's the cycling trajectory that we used, and I'm zooming in. Those papers have tons of results if you want to access them. We have scenarios running with wind, with solar, and scenarios based on data from PJM market. Those are open source data, so we got some Duke power plants profiles that the controller could follow for power generation. So that SCPC plant that I show, we're using about 9 inputs and 9 outputs for the control. However, of course, it has hundreds of or thousands of states, right? Because we're talking about just input-output control. You have the cyclic profile here. You see the linear DMC struggles a bit. The other ones are pretty good. I mean, we perform really well. And the challenge, of course, with the linear MPC is that you have to linearize around a certain design base load point. The base load point is about the 600 megawatts. So as you get away from that, the linearization point is further away, right? So it causes some linearization errors there for a model prediction. And the MPC, of course, is very much model-based, right? And you see all the other controllers perform really well. In the paper, we showed that this solver that we developed is faster than other traditional solvers that we have used as benchmark. The second example is a subcritical coal-fired power plant. This is in MATLAB, Simulink. And this model was developed by Salome Aglisi. He is at NETL now, and in collaboration also with Daniel Castring. And I will also acknowledge them as well for this. And they have developed a simplified model to start with the subcritical coal-fired power plant, and where you have the superheaters here. And we have a 3x3 control structure where we have the different temperatures of the primary and the final superheaters as the U1 and U2 here in your system. And we also have the valves as our input variables, the spray valves, and the cold flow rate there. So this is a preliminary system. We are actually working as well now to develop some more high fidelity models for this application to work with the Hyper team on a separate project on state space and online system ID, and also on adaptive control. So that's kind of one of our ideas moving forward. So here is the subcritical coal-fired power plant cycling scenario. This data that we obtained was from ERCOT in Texas. It was in January, okay, so don't worry about it. It was before the issue that happened there. And we had some data for this winter power plant. And the interesting fact here is that we have an OSI Pi, I guess it's a Viva Pi now, server in our office, in our group there, in the computation infrastructure at WVU, where we can upload or take this data directly from power plants that are online. So this subcritical plant has online data being available. I guess it's aggregated data, right, for safety purposes. But then we can take this data real time and try to see if our controller and our model would follow. So you can see here we can barely distinguish the set point with the actual process variable. So this MPC performs really well. We use here a quadratic DMC controller with the MPC toolbox that we developed that I showed before. We also put some regulatory control here on the temperatures, and you can see that they stay well there around the set point. I don't know if I covered the 10 minutes, probably close to that. So just to close the presentation here, I would like to thank the US-China Clean Energy Research Center, the CERC program. It was very large. It was about a 10-year effort that funded this work and graduated. We graduated a couple of students and built some collaborations there. And it's funded by US DOE headquarters. And I also would like to thank, of course, the people who do the work. Rasheen, as I said, is in National University of Singapore. I believe Paolo met him, had extensive discussions with him about Mpc. Daniel and Salome is at ADTL currently, working full-time there as a PhD student. Still needs to defend, though, but is working there. And I would like to acknowledge, of course, the funding support here from DOE and Paolo for the invitation, and Dave for the invitation as well. Okay, thank you all, and I'll be happy to share any other thoughts or answer any questions.
Thank you, Fernando. If you have any question, you can unmute yourself and ask a question. Otherwise, you can write the question in the chat. Let me say one more thing. Like you mentioned, we have a project with Dr. Larry Shadle is the PI of the project. We are establishing a four-way CREDA between AIMS, NETL, Southern Company, and EPRI to implement and test an adaptive Mpc. So you mentioned that. I need to reinforce that that project. So if I don't see any question in the chat, so maybe we can go to the next speaker, and we can have an open discussion at the end. So Steve, are you there?
I'm here. Can you hear me?
Yes.
Excellent.
Okay, so let me introduce Mr. Steve Sichman. Is the program lead for the process controls and automation program at EPRI, program 227. His program is part of the enabling technologies group within the generation and low carbon resources sector at EPRI. His interests include advanced and adaptive controls, instrumentation, and data analytics. Steve graduated with a bachelor and master degree in the mechanical engineering department at the West Virginia University. Steve was part of the NETL family in the past. He was a researcher, a project manager, and he became the acting technology manager for the cross-cutting research program. Steve has over 16 years of experience. So Steve, whenever you're ready, please go ahead and start your presentation.
Will do, Paolo. Thank you very much, and thank you for this opportunity. I think we're going to be flying through these things just as our previous speaker did, but just wanted to give you, some of the drivers. I think we'll be preaching to the choir a little bit there, but we'll talk about that a little bit, and then we'll talk about some of the recent activities we've done at EPRI and some opportunities to participate with us, in the future. So I think we've talked about it a good bit. Operational flexibility is one of the main reasons that controls continues to be very important in these power plants, be it in more emerging power systems or with the ones that are existing out there in thermal power. But they're looking for more consistent, but also more operational flexibility in that consistency from operator to operator while optimizing their O&Ms. As we know, the workforce is continually changing. New people are coming in. They aren't as experienced as the previous ones, or they're asked to be cross-trained much more than they were in the past. So they don't get that expertise that they had in the past. So they want to leverage that expertise as well as they can, as well as optimizing their O&M costs as they move forward. So that really works with that consistency of operational flexibility. We got to make sure that these plants continue to be cost competitive as we move into this energy transition with the addition of renewables. We want to make sure that they have frequency response addressed as much as we can as that, as renewables continue to be a bigger percentage of the portfolio. And we need to do this all, as I said, with a workforce that is continually changing. So not only do we need to have these great controls and advanced controls out there, but we need to make sure that they get proper training to understand that control. but also that they can manipulate it as much as they can on their side, be comfortable with it, and understand what's going on with it. So that's something that we've seen that's really important on the EPRI side and the utility side as we're working with those utilities. It's not just how cool and how great can this work, but it's also can we understand it and can we change it as it's needed. So just a quick overview of how we're doing that within the process controls and automation program at EPRI. I think our objectives are pretty well aligned with academia as well as with the utility industries, and that's looking at opportunities where advanced process controls can really improve upon flexible operations. So I mean, that can be this model predictive control that we just heard about. You'll see a demonstration of that we evaluated that a couple years ago, when we were able to travel. So and hopefully we can get that stuff ramped back up. We're looking at automation development and solutions. We know that there's lots of automation that is available within current DCS packages, but we just have to make sure that we get those proper function groups, make opportunities for the operators to be comfortable in those automation procedures, so they have to look at less variables, so to reduce their operator burden while they're trying to do more and more startups and shutdowns and do them more consistently. But also we're providing the opportunity to look at improvements in their existing process control systems. So just make sure that their DCS systems are ready for this flexible operations, that they have some of those common packages that are out there, using feed forwards when that may be all that's necessary if it's not super complex, or some of the other packages that and control loops that are available within their current DCS. Also, during these flexible operations, we have to make sure that we're doing a good job of alarm management. So we're looking at logic techniques that will change as you go through different profiles of that or different missions of that particular plant. So we have to make sure that alarm management is well taken care of, and once again, reducing the operator burdens during those flexible operations. You can have the smartest controls in the world, but if you only have one leaky dumb actuator, it's really not going to help out that much. So we are looking at improved actuation techniques, looking at VFDs a little bit more, and making sure that we are using them where appropriate, and also just making sure that the utilities know that there's certain times that hardware has to be the answer, and controls can't help once again a leaky actuator that it doesn't seem to be working, or a valve. Other things we're looking at is controllability of emerging power systems. We know as fuel changes come out, as well as the grid becomes more and more integrated, we're going to have to start looking at challenges around controls of those. When batteries start coming in, that's a very nonlinear function. Making sure that we can incorporate those as well as possible, and squeezing out as much efficiency as possible in these low carbon processes. And as I talked about, it also is an optimization problem as the fleets are looked at more holistically. We have to make sure that we're optimizing the power output from these plants as best as we can, incorporating the flexibility that we previously discussed. So how are we doing that at EPRI? We're doing that through plant demonstrations at actual plants with member participation. So that's kind of a, hey, first of a kind or second of a kind, hey, we want to do this, we want to evaluate it hand in hand with you and show the benefits. We want to show the challenges. We want to show if it wasn't beneficial. Sometimes that's one of the benefits that we have at EPRI as well, is we can work hand in hand with them. And they're like, it worked well, but it took, 18 months to set up. It required a lot of IT. We just don't think that that's viable at this point. Maybe one of the things that we need to do is figure out more streamlined ways of getting it implemented. Of course, as we talked about with this workforce transition, it's on-demand training. So guidance documents in some of these, modern controls, what's out there, tuning techniques, those type of things, as well as innovative product delivery. So we have a lot of online courses that we can offer through EPRI-U, not just within controls, but that's one of the things that we're looking to grow as a controls library, kind of a controls 101, and then specific components, as well as specific types of controls that can benefit in those specific components. And then the other thing that we're pretty excited about, and we're looking at ways to work with utilities as well as with NETL and academia, is through our EPRI research simulator, through some of these demonstrations where we wanted to evaluate it on their high fidelity, operator training simulator prior to incorporating it at the plant. There was obviously logistical concerns that came into that. I mean, its main function is to train operators. Sometimes they didn't want us messing with it because it was a brand new toy, things like that. And we developed a pretty high fidelity simulator that's very flexible. It probably sacrifices a little bit of that fidelity for flexibility, but it's a really good first step in looking at some of these more novel and emerging controls techniques. It looks and smells a lot like some of the vendors that are out there, some of the control blocks that are out there link in, much like some of the vendors that are out there, but it is run through a common platform in MATLAB. So it's remotely accessible. It's something that, if you're a contractor on a project, we give you access, you get a username and password, and then you can use the simulator. So it's something we're pretty excited about, and it's a way that we can do a really good first step prior to moving towards those plant demonstrations. So just touching on some of the ones that we've done in the recent past, the first one is the steam temperature control strategies for combined cycle units. So steam temperature control has been a big issue in coal and combined cycle units alike, especially in these flexible operations. So we evaluated multiple controls techniques with a utility that eventually allowed us to incorporate it into their actual combined cycle unit. We did a 2x2 Mpc, a model predictive controller, had many benefits. Once again, we worked with the vendor hand in hand to say, hey, is this what you would do in this particular circumstance? How would you go about, tuning that? This is how we did it. Does that seem, viable for you guys? We were able to successfully implement that model predictive controller on one of the reheat lines and show the benefits of how tight it could control the temperature through startups, through transients, whatever it was, and also it had a saturation prevention limiter, which can cause a lot of issues on the bottom end of it of overspraying. So we were very excited with that. We were able to win a tech transfer award. The plant was very excited to the point that they're actually looking at incorporating it into all of their reheat and superheat lines. So for steam temperature control. So that's one. And you see these long numbers up here. If you go to EPRI.com and you type in that number, it'll take you right to the report, give you a general idea of that if you want to get a little bit more information on that. The second one was looking more at what's already in your existing toolbox around process control strategies to improve low load operations. EPRI's done extensive work around best practices and operational techniques, but stop short more often than not saying this should be incorporated into the logic. So we kind of grabbed that baton and took it forward and say, well, let's incorporate this into the logic and see what we can do. So for a coal-fired unit out west, we were able to incorporate 6 different controls improvements that were implemented, including sliding pressure control to improve their low load operations. We were able to provide a lower stable minimum load. They were seeing vast instabilities in their low load operations prior to incorporating these, but we were able to fix some of those through some calculation changes, and once again some standard tuning exercise and stuff like that, optimizing the controllers that they had. We were also able to improve their efficiencies at those minimum loads and also improve the ramp rates coming out of those minimum loads back to base loads. So something we were pretty excited about. And then the last one that we've been able to get started on, we completed the report in 2019, and we've actually done some implementation tests through all this crazy stuff because we've been able to do some recommendations based on trending and data provisions. But what we were looking at is, okay, well, we know that people are looking at centralizing operations or using the staff that they have as best as they can in an optimal way. Can we increase the automation at these plants? How can we do it? So we provided a guidance document around options, approaches, and practices for increasing automation in thermal power generation, but also this can be applicable to some renewable generation such as hydro. And we also developed a readiness index where basically it has multiple categories that we've weighted along the way, and we say, okay, that based on your instrumentation, based on your control logic, based on what type of plant we're looking at, the complexity of it, these are the places where we can automate quickly. These are the systems or subsystems that require some a little bit more capital funding, before moving forward with automation. And as I said, we've had several members come forward and say, hey, we want to go through that readiness index development with you on this particular plant, and we've provided findings to them as we move forward, and they're working with their internal folks to make those recommendations and say what they can afford, what they can't afford, what they're comfortable with, and moving forward with that. One of the other things we've been looking at this year is exploring plant control strategies to support grid frequency response. We know once again as the penetration of renewables becomes higher and higher, the need for frequency response on the thermal generation sides become greater. So we're looking at the areas where there's some low-hanging fruit, some standard practices that you could look at for incorporating into your control logic to improve your frequency response, but also the gaps, so we can start looking at those within the EPRI simulator and saying, okay, here's some scenarios, here's what we can go after, here's the things that we need to do research on, and here's some control strategies that we've developed internally at EPRI. So that's something that we've started this year. There's going to be a presentation that basically is a deliverable for this year, and then the final report will be released in early next year, along with some simulation results to say, hey, here's where you were before. Here's through the simulation you can show that we can get improved frequency response with these control strategies. Another one that we're pretty excited about is this digital demonstration facility. Through a lot of the work we've done on plant digitization, we've noticed that there's some one-off demonstrations that we can do. One of our members came forward, and many of them brought up the need, but one of them came forward and said, look, this is all great that we're seeing kind of these stepwise improvements or incremental improvements, around plant digitization, but we really need to understand what type of infrastructure is needed, how much that's going to cost us, and what's the benefit on the other side. So they offered one of their units to us, which has both coal and gas assets on site, to look at analytics, advanced control techniques, automation techniques, as well as instrumentation to move forward. You can see that there's multiple utilities involved, 12 total projects going on right now, multiple collaborations through universities, EPRI's, national labs, technology providers, and OEMs. Very excited at what we're able to do with this one. Once again, I'm just trying to skip on the surface of it, but it's a collaboration opportunity that we're pretty excited about, that we've been working forward in. And once again, there's some advanced controls projects going on that are around evaluations for steam temperature control and drum level control for model predictive control, as well as some automation evaluations. And then the last one is this Intelligent and Autonomous Plants Grand Challenges Working Group. EPRI saw a need around their internal AI initiative to really get to the point of 5 main areas where we could look at grand challenges for incorporating AI into the energy sector. And one of them, which I'm the lead on, is this Intelligent and Autonomous Plants Grand Challenge Working Group. We kicked it off at the end of September. We're looking at having monthly meetings where we basically just share ideas. We identify collaboration opportunities between the working group. The initial folks, we had about 40 people come forward and say they wanted to be part of the group. The meeting had, I think, 60 to 70 people attending. It was multidisciplinary. It was a great kickoff meeting. We had some passionate people in there, similar to this, what's going on within LEAP. It's free to participate if you have some interest in that. Just please let me know. It's actually co-led with Kelly Rose from NETL. So it's once again another great collaboration opportunity between NETL and EPRI. But once again, we're allowing folks from OEMs, universities, wherever it may be, that's involved in this type of realm. We'd love to have you on the call so we can identify those collaboration opportunities. So if you have interest, please let me know. My contact information's on there. And I've probably gone way over, so I'm going to stop talking now. And thank you for your time. Thank you.
It's good. Thank you, Steve. Anyone has any question? Let me ask a quick question on the testing of the Mpc. So what's the most challenging thing that you had when you tested the Mpc? The implementation, the tuning, like you mentioned. What's your opinion on that?
So within that, in all fairness, a lot of the issues had to do with working within the confines of the vendor. There's certain things that Mpc, it was non-adaptive. It was, once again, a 2x2 Mpc. It did great on disturbance rejection, but figuring out what 2 inputs and 2 outputs were the most dependent was a big issue on there, because the plant had some nonlinearities going into different modes with the gas turbine. Those type of things really changed what we thought were the dependent variables. And then we do something else. We're like, nope, that changed it entirely. So really trying to nail down those things within a plant that was a little older, and once again really benefited from that MPC, but really working with that was some of the challenges that we ran into. But like I said, but the tuning of it was pretty straightforward. I mean, with we used a system identification toolkit within MATLAB to kind of get the tuning parameters after we figured out those 2x2s. We were pretty good to go.
Okay. Thank you. Thanks a lot for your lesson learned. Let's say that.
Thanks, Paula.
So I don't know if Dave, you have any question on the actuator. Steve mentioned that actuators are also a problem. If you can have the best control strategy, but if your actuator is pretty slow, yeah, you don't have the response that you expected. I know that you have another project with University of El Paso and also with Thomas Ains from Georgia Tech. I don't know, Dave, if you wanna share a little bit that experience. You're muted now.
So Paulo, yeah, I don't know if Comas is online, but yeah, I don't want to take up a lot of time going into all those issues. I know you have, 4 more speakers to go. So.
Okay.
But thanks, Steve. I appreciate it, and certainly we can bring up some of these questions in the last session because it'll be open to a full discussion of all the speakers.
Perfect.
Okay. Thank you, Steve. Thank you, Dave. Let me go to the next speaker. The next speaker is from the University of Genoa. Dr. Luca Mantelli is an associate researcher at the University of Genoa working on simulation dynamics and control of innovative energy systems. Luca got his PhD from the University of Genoa. He was a visiting researcher at NETL in Morgantown, and he also collaborates on multiple international projects with university in Sweden and in Europe in general. He's currently working on control strategies to improve the flexibility of combined cycles and on the development of dynamic models for training of operators in a virtual reality environment. He's also collaborating with Rolls-Royce within the University Technology Center of the University of Genoa. So, Luca.
Thank you, Paolo. So I'm going to share my screen. Okay, can you see it? Okay, so in this presentation, I'm going to show the approach of the University of Genoa for controls for novel concepts in the European projects where we are working. So the first project that we're going to see is the PAMPIT project. As Professor Lima was saying previously, now in the grid, we have a growing presence of non-dispatchable renewable energy sources. And this requires to the combined cycles and traditional fossil fuel power plants to increase their flexibility or to extend their operative range to stay competitive. And so the goal of the PAMPIT project, which is a European Horizon 2020 research project, is to study and develop innovative strategies to do this. And it's a project that involves 14 partners from 8 different European countries. And it is the goal of this project is to integrate the combined cycle, which traditionally is composed by a topping cycle and a bottoming cycle, with additional equipment, in particular heat pumps and thermal energy storage controlled by advanced control strategies. There are 2 different layouts which are studied within the project, one oriented only on the generation of electrical power, and the other one instead for a combined heat and power combined cycle. So in this presentation, we are going to see the power-only configuration, but the approach used for the control is similar. So in both these 2 layouts, the ultimate goal is to condition the compressor inlet air temperature with the heat pump or with the thermal energy storage to change the power output of the combined cycle and extend its operative range. So what we can do in this case is to cool the air with the thermal energy storage, to heat the air with the heat pump, and to charge the cold thermal energy storage or to cool directly with a heat pump. So the control system is structured as a 3 levels control architecture, which is implemented in MATLAB Simulink. There are 3 levels, and each one has a different time scale and accuracy. There is an offline high level, which is run the day ahead to plan all the day after operation. Then there is an online 15 minutes controller, which is a thermodynamic optimizer. And then there is the low level, which is a model predictive control running in real time to control the heat pump and the thermal energy storage. So here we can see a bit more in detail these 3 levels. So the scheduler generates the schedule of electrical power of the combined cycle, of set point of electrical power of the heat pump, and the operative condition of heat pump and thermal energy storage for the day after. So the operative condition is represented by this flag 1, 2, 3, 4, which corresponds to these conditions. It is based on historical data of the Moncalieri plant of Iren, one of the partners of the project, then on performance maps of this plant, and on the Italian market for what concerns prices and fees of the energy market. And what we get is a schedule of the whole day after. Then there is the intermediate level, which is based on a simplex optimization algorithm that determines the operation of the plant, and its main purpose is to correct the schedule based on the real conditions of the plant. An example that we can make is that if the scheduler planned for the next 15 minutes to use the cold thermal energy storage to cool down the air flow, but the actual state of charge of the test is too low, this controller switches from cooling with the test to cooling with the heat pump. Then we have the low level, which is an Mpc integrated with an observer. It is designed as a multi-input, multi-output Mpc, and it controls the thermal power of the test and the electrical power provided to the heat pump in order to minimize at the same time the mismatch on the electrical power generated by the combined cycle and the electrical power set point of the heat pump. Of these, there is an optimization function, so a cost function that includes these 2 terms, and the mismatch on the whole generation is the one with the highest weight, so it has a higher priority. And the MPC uses state-based models of the heat pump and the thermal energy storage to predict the impact on the whole system. So this system was already tested in a model-in-the-loop setup. We can see here on the left some results where all the 3 levels worked as intended. And the pump heat approach was able to extend the operative range of the plant. So we can see here that there was a power demand that was higher than the nominal maximum power of the combined cycle. So the scheduler planned a cooling of the inlet air with the heat pump. Doing this, it was possible to increase the maximum power output of the combined cycle and to match the demand. Right now, we're working in our lab to test this also on the real equipment. So the control is already integrated with the pump heat cyber-physical emulator plant of the University of Genoa, and it will be tested soon. The other project we are going to see is the Robinson project. So the control approach is similar, but the purpose is different. The Robinson project aims to decarbonize islands, relying on an intelligent energy management system, integrating the local consumers with renewable energy sources with the use of biomass and also relying on industrial symbiosis and innovative technologies. So it's also this one is an Horizon 2020 European project where 18 partners from 10 different European countries are involved. And it is a project focused on islands. So there is one demo island, the Egeroy Island in Norway, and 2 follower islands, which are the Crete Island in Greece and the Western Islands in Scotland, which are going to be studied as simulated case studies. So every island needs a clean, cost-efficient, and reliable solution that must be tailored to fit their characteristics, which are very peculiar. For example, the local economy. For the Egeroy Island, it is an island with a strong fishing industry. And so the Robinson project is going to study this approach using the local fishing industry, which is Prima Protein, one of the partners, as a source of biomass. So regarding the energy management system, in this project, we combine our experience from the Pump It project and our experience on the management of smart grids. So also in this case, we have an energy management system that controls the prime movers, so the generating systems on the grid. And then we choose in real time the optimized strategy that makes it possible to minimize the operative expenses and to match the user demands. Also in this case, we have an offline scheduling tool, dynamic modeling of the systems in the grid, and a real-time optimization and control tool. So we can see here that the structure is similar to the one of the Pump It project. We have an optimization algorithm that defines each prime mover operation every 15 minutes, this market function, using the demands of electrical and thermal power, the cost, and a daily scheduling. And then we have a multi-input, multi-output MPC that controls each prime mover, updating the signal every second. And then we have a feedback on the actual state of the grid. We can see here a bit more in detail which are the users and producers involved. We have here our control system. The control system determines the operation of combined heat and power plants, of thermal power generator, and if a connection is existing, it also determines if current can be traded with mainland grid. Then on the island, we assume to have also solar and wind power generators, the local microgrid, and then from the industry, we also provide heat for the local thermal grid. So we are starting to study this approach, and the project will be developed in the next years. So this was everything from my side. So thank you.
Thank you, Luca. There is any question from the audience? Anyone has any question? I don't see any question on the chat. I think we still have a few minutes for one question. Let's see. So how do you go ahead?
Yeah, so I'm Taryn Vincent, Colorado School of Mines, and I was wondering, so in the Pump Heat project, so if we think of it as a storage system, or can we think of it as a storage system in which you can effectively store electrical energy or displace,
yeah, a bit, yeah, because with the thermal energy storage, for example, when you're heating the inlet of your compressor, you're not just doing that. So doing that, you're able to reduce the overall power generation of the combined cycle, but you're also using the other side of the heat pump to store cold energy in the thermal energy storage, so that when you will need to increase the power output of your combined cycle, you'll be able to use that energy. And so these, yes, sorry.
So yeah, what sort of capacity? So if we think of energy capacity, what sort of capacities are possible? Is it just limited by the storage size or the tank size?
Yeah. So how much we can store? Yeah, I would say it's limited by the thermal energy storage size.
Mm-hmm.
Yeah, for sure. So it depends on the configuration you're going to adopt. The scheduler, so the higher level in the control structure, as inputs all the characteristic of the plants. So when you schedule the operation of the plant, you give us information, the size of your thermal energy storage, and based on that, it determines which is the best condition to adopt for a certain hour in your next day.
Yeah, thank you.
You're welcome.
Thank you, Professor Tyron. I think now we need to move to the next speaker. Thanks a lot, Luca. If you can stay until the end, so maybe we have other questions. Okay, our next speaker is Dr. Michael Springle from C0. Mike is a senior research engineer at C0, where he leads the modeling and simulation group with a focus on supporting innovative clean energy technology through detailed dynamic system modeling and advanced control strategy development. Mike holds his PhD in engineering from University of Purdue. While at Purdue, he worked at the Maha Fluid Power Research Center, where he focused on the design, simulation, optimization, optimal control, and testing of novel energy efficient hybrid powertrains for both on-road and off-high-road applications. So Mike, if you are ready, you can share your screen and start with your presentation.
So, thank you, Paula. Can you see my screen now, or?
Not yet. We can see you, but we cannot see your slides.
Perfect. Can you see it now?
It's loading. A few seconds. Okay, now we can see your slide. If you can go to full screen, that would be great.
Does that work now?
Perfect.
Perfect. Okay. Well, thank you, Paolo, and welcome everyone. My name is Mike Springle with C0, and today I'll be talking about some control strategies for an integrated SOFC GT system. So C0 is part of an integrate program. As Scott mentioned this morning, we're developing a system along with Nexteris. Nexteris is the PI and is the fuel cell development experts. Braden Energy is going to be our turbo machinery experts, developing custom turbo machinery, as well as our recuperators and the combustors and the like. And C0 is operating as the overall integration partner. So we're doing all the overall system level design, analysis, and then building the system, doing the controls development and testing it in our facility as well. Now, as Scott mentioned this morning, we're only in our first year of the project. There's been a lot of great presentations over the past few days, a lot of really advanced control strategies. We're not quite there yet. So I think what we're going to do is just present a high level overview of kind of our system and what we're finding today. As part of that, I'm going to walk through kind of very basic to start with how the system operates. I know a lot of you are probably very familiar with these systems, but perhaps a few of you aren't quite as familiar. So if we look at how a system operates, and this is the general topology of the system we are developing, but we have omitted a number of components for IP reasons here. But what we really do is we start by supplying, once the system is kind of up in operation, we start by supplying fuel into the system. The stacks themselves convert fuel into electricity at a very high efficiency. That's sent out to our power electronics. But the stacks themselves don't consume all of the fuel. There's still a percentage of the fuel passes through the stacks and goes on to the combustor. The combustor then combines this fuel with pressurized oxidant, generating additional heat, which flows to the turbine. Now the turbine is able to extract a large percentage of the available power and produce mechanical rotational power, which then flows through the system. The compressor takes a large percentage of that, and whatever remaining is sent to a generator, which produces additional electricity. And we combine those two electric streams, and we'll export them to either a grid or an islanding configuration. As I mentioned before, the compressor does take up a large percentage of the power generated by the turbine. We need that power to produce the motive force to move the fresh oxygen stream and pressurize it throughout our system. Additionally, while the turbine does extract a large amount of the energy from the combustor, there's still some remaining. And so we have included a turbine recuperator, which allows us to transfer the majority of that additional heat from the turbine outlet into the incoming cathode stream. And this is important because our stacks are operating somewhat hotter than others, between 750 and 850 C. And in the stacks themselves, they are somewhat exothermic in nature. So as the cathode flow passes through, it's going to pick up some additional heat, which is then going to flow to the combustor. So at a high level, this is kind of how this system operates. Now, if we kind of look at some of the states and controls, for the states, we've got power output, not, I guess, traditionally a state from a controls perspective. I'm going to leave it in here. The kind of maximum SOFC temperature, as well as a turbine inlet temperature. We see these as some of the key states. And in order to influence those states, our controls are going to be fueling rate, the electrical load, the resistance placed on the stacks, as well as the speed of the turbo machinery. Now, as we've been designing the system building up, one of the items we chose to de-risk the controls portion is actually to put the speed control on the power electronic side of the motor generator. So with the system we are building, we're going to be able to command a speed, and the motor generator is going to be able to hold it there very accurately, whether it's motoring or generating. So that kind of really simplifies some of these control aspects here. In order to support our overall system design and controls development, we put together a high fidelity dynamic system model. This was built kind of from the ground up based on governing equations in MATLAB Simulink. High level, it's using real and ideal gas properties. We've got individual species tracking for 9 species. We're doing equilibrium chemistry on our methane steam reforming and water gas shift, as well as all the electrochemical reactions and combustion and other things. Additionally, we have it now running quite well and quite fast, and we are currently using this as part of our mill development effort, and we're going to use it as kind of software in the loop as well, and really to validate a lot of these control strategies before we actually apply them to our system. Now, in using this dynamic system model, we ran through a number of different cases. Again, we're kind of just starting out here, so trying to understand how can we best optimize the system? How can we use it most efficiently? And here's a couple of the takeaways that we found. And this is really specific for our system and sizing. But in general, the higher the SOFC temperature, the more efficient the overall system is. Similarly, the higher the turbine inlet temperature, the more efficient the overall system is. Now, both of these are limited by mechanical constraints, thermal constraints on the system, but we do want to maximize both of these states in order to maximize our overall system efficiency. Another important item that we kind of noted as we're going through the system analysis is that the flow from the compressor really helps to reject a lot of heat from the stacks, and heat rejection from the stacks is really critical. If we don't pull out enough heat, it severely limits our ability to produce more power because that reaction is effectively exothermic, or any losses, aromatic losses, and all the other losses effectively get converted into heat, and that needs to be carried away. Otherwise, we would overtemp our system. So now let's talk briefly about one example case here. So let's say we're running steady state at 80% power and we want to increase that to 100% power. The first thing we'll do is we're going to increase fueling to our system. Actually, sorry, I was skipping ahead a little bit. Forget which slides I had. So if we look back at our principal control loops, based on our findings here, we want to put in 3 principal control loops. So the first is adjusting our fueling rate to control our power output, as you see here. Pretty basic. The next one we identified is we're going to have our controller looking at the maximum temperature. Flowing more gas through the stacks is going to help transport additional heat away. So now the stack temperatures are going to start to fall. As those stack temperatures are going to start to fall, our SOFC temperature controller is going to kick in, and it's going to start increasing the electrical load in order to generate more heat within the stacks in order to bring that temperature back up to its set point, which is then going to result in less fuel flowing out of the stacks into the combustor, which then ultimately is going to reduce the turbine inlet temperature, and we're going to slow back down. Now, as we've been kind of going through and running this through our dynamic system model, we found as long as we keep those transients under control, we don't have large step changes in our requested power output, and our controls are reasonably well tuned. This is actually seems to be a very stable control strategy. We don't see a lot of fighting back and forth between these different control elements here. And so, I think this is kind of our base implementation we're looking at as we're kind of exploring the system, trying to understand how it operates. I think in the final implementation, I'm sure it's going to be more complex. We'll probably put the majority of the control effort actually in feed-forward terms, use these feedback loops as a much smaller percentage of the overall control effort. Another thing you'll notice, I haven't necessarily been talking about fuel utilization ratio or the power split between my turbo machinery and the stacks, or my current density. All these are important, but we found that they really kind of drop out of how you decide to size a system. For example, what's your stack area relative to your overall power output? So at a high level, this is kind of where we're leaning right now as we start exploring the system, and we will continue this in the coming year. So kind of moving on to the last portion and switching topics slightly, is some of these energy storage concepts. So as we've heard, kind of multiple times over the past couple of days, energy storage is really going to be probably critical in this system, and we certainly agree as well. So we're looking at a couple different options. So the first one is going to be electrical energy storage via batteries, and I think this really helps out a lot because the batteries themselves can take up the short duration demand transients from the grid. This is especially important if we're, let's say, operating in an islanding configuration and our SOC GT system needs to respond to external loads. So rather than having our system, the more complex and slower to respond, SOC GT system respond, we respond to the batteries. This then allows decoupling really of the SOC GT system from the grid and allows us then to have a power management control that's going to more slowly slew the power output from our system to what the grid requires, and also make up or deplete the batteries to get back to your original SOC. Another very interesting concept brought up by the Nettle team is thermal energy storage. There's a lot of system thermal mass in this system that can be utilized here. So then it really comes down to how can we best balance the power? What I previously presented in terms of just maximizing the turbine inlet temperature, maximizing stack inlet temperature, that's really instantaneous optimization. That's very easy to do. If you have these multiple other energy sources, this becomes much more complex. So what we may look at in the future is something that is very close to my background in the power management of hybrid vehicles, and it's dynamic programming. And if you're not familiar with dynamic programming, it's a very powerful tool. It guarantees global optimality down to the level you discretize the system to. The example over here is for a hybrid vehicle. And it allows you really to determine the maximum possible performance. It doesn't take into account how you think the system should operate. As long as you're not violating any constraints that you've imposed on it, it's going to find out what the absolute maximum system performance is, what the absolute best way to control the system is in order to meet whatever metrics you have set for it. A lot of times you can discover some very unique and effective control strategies, but they may be counterintuitive, right? You may not actually think to control it this way, but it turns out to be really quite effective. And so dynamic programming is really considered the gold standard in power management. It's very useful for baselining other implementable control strategies. And as good as dynamic programming is, one of the key drawbacks is it's non-implementable. It requires a priori cycle knowledge. So effectively, if you know the future, you can design a perfect controller. So what this allows us to do, though, is as we're kind of developing these different power management strategies, we can feed in a complex, power demand profile, run it through, and it'll tell us, what the best way to operate the system is. we can then build up various suboptimal power management control strategies, kind of really leveraging the lessons learned from the globally optimal. It allows us to benchmark and see, how close are we to this? Is it a controls limitation? Is it a system limitation? So, all right, well, thank you for your time. If we have any questions.
Thank you, Mike. Thank you very much. Nice presentation. Anyone has any question? I have a quick question on the turbine. Do you have the opportunity to measure the turbine speed? Because I see that you are trying to control the turbine temperature. At the Hyper, we had the opportunity to measure the turbine speed with optical sensor. I was wondering that if you have the same
Sure,
thing.
yeah. So I mean, what we will do is we're going to have motor generator, connected directly to this turbo machinery, right? That we are designing it such that it is going to be integrated with appropriate encoders or, I guess whatever feedback that the control system needs to actually, motor controller needs to actually control that. Will be incorporated into that. So we should be able to basically command a speed, and this can go up to well over 100,000 RPM. But we have a high-speed system available to us. So yes, we will have closed loop control over the speed. I think having control of the speed really simplifies things versus trying to control that speed based on fuel or some of these other metrics. Additionally, Brain is designing custom turbo machinery for us for this application, so they're able to take into account all the pressure drops kind of throughout the system and both optimize the turbo machinery for this application, but also provide us with greater headroom to prevent kind of the surge events that I know are often problematic if you try to just take an off-the-shelf piece of turbo machinery and then significantly increase the resistance between the compressor and turbine.
Okay. Thank you. Mike, I see another question in the chat. Maybe you can reply to it, or we can discuss at the end. We have two more speakers.
If I can figure out how to see the chat.
Okay.
So
okay. Anyway.
CL, maybe you could just go ahead and unmute yourself real quick.
Yeah, sure. Thanks, Dave, and thanks. Very great presentation. So my question is about your fuel cell model. I'm wondering, is your fuel cell model is a distributed model or like a zero-D lumped model?
Yeah, absolutely. So we base the model. I apologize, I'm going to miss a couple of the groups here. I think it was I don't want to actually mention the groups that we leveraged, but it was a couple of PhD theses because I think I would get the people's names wrong. But it is a distributed parameter. Right now we're discretizing it into 7 elements, kind of along the length. We're starting with the kind of nurse potential and then kind of calculating your ohmic losses, your activation losses, your concentration losses, pulling all those out. We have a solver that we coded in there to take and basically loop through the current density on each one of those kind of discretization elements in order to stabilize all 7 of those at the same voltage. And that model also takes into account all of the kind of onboard reforming as well, all of those reactions. And all these components, we do have the thermal mass and everything included in that, and we're using compressible flow.
Right. So I'm also curious, like when you do like load change, do you have a fuel cell temperature distribution, and or in other words, do you know like the temperature gradients here?
Yes, absolutely. So relative to the discretization of the inlet outlet temperatures and then those 7 intermediate temperatures, I believe Nettle has maybe 20 or so. Again, we were trying to balance computational efficiency with fidelity, which is kind of why we land on 7 seemed to be a good match. We could certainly increase those, but yes, we certainly do. I guess then the question comes is, how rapid of transients can we get, right? But we are certainly monitoring the kind of degree C per centimeter as well as kind of the degree C per second type metrics as we're looking at this. But that really kind of comes down to, I guess, how quickly our load transients are. And at this point, that's something we really haven't necessarily gotten into in this project, but we certainly plan to as we move forward.
Great. Thanks.
Thank you. Thank you. Thank you, Mike. I move to the next speaker so we can maybe have another discussion at the end. Thank you a lot. Thanks for your question, Biao. So our next speaker is Professor Tyrone Vincent. Professor Tyrone is a faculty at the Colorado School of Mines University. He's currently a professor in the electrical engineering department. His research interests are in the system identification, estimation, and control, with collaborative work in a wide variety of applications. These applications have included chemical and physical vapor deposition, welding, augmented reality, energy efficient building, fuel cells, fuel processing, and batteries. It also has a lot of interest in nonlinear system identification, constrained moving horizon estimation, and robust model predictive control. So Professor Tyrone, whenever you are ready, you can share your screen and start your presentation. Thank you.
All right, sorry, I have to make a small adjustment here.
Yeah, we can see your slide. Can you please go to full screen?
Yeah. All right, so
now it's good. Thank you.
All right, great. So I'm unfortunately, I apologize. The presentation is set up to play. I didn't realize the presentation was set up to play automatically. I can try this again. See if this works. So so this is part of the RPE Integrate project that Rob Braun spoke about in the earlier section.
Sorry, Professor Tyrone, we don't see your slide.
You can't. Oh, you can't see the slides. Okay, one more time.
Okay, now it's loading. Okay, we can see your slide. If you go to full screen. Perfect.
All right,
Thank
you. Sorry about that. Yeah, so I'm Tyrone Vincent at the Colorado School of Mines, and I really appreciate being at this workshop. A lot of really interesting presentations. So this project, so Rob Braun gave a kind of introduction to this project in the morning session. So it's a large project with a lot of contributors, both at School of Mines, also Colorado State University, Kohler Power, and Air Squared. And so in this case, this is a hybrid fuel cell system that is integrated with an internal combustion engine. And so we can look at the kind of a diagram of the system here. It's a bit simplified, but the major components are here. So we have a pressurized solid oxide fuel cell system, fuel cell supplied by series power. The anode tail gas is sent to an internal combustion engine that the internal combustion engine will drive a motor. In this case, we're actually showing the motor is also connected on a shaft with a compressor and expander. Although there's different configurations that we're considering. The compressor will compress the cathode air and that is supplied to the SOFC, and then it's expanded, that anode, the cathode exhaust is expanded out to recover the energy. So some of the components that are not listed are we have a pre-reformer and heat exchangers, and also some supplementary heaters that would be used during startup, and and in low power operation. So one thing that is a little bit different, because we're using positive displacement equipment on the compressor and expander. So that does simplify the control process a little bit. We do have to control speed, and we have a pretty good idea of what the flow is going to be. Also, with the internal combustion engine, in terms of the control development, of course, the engine itself has control that needs to be implemented. But in terms of the larger system, it's gonna. I mean, it looks mostly like a pump, so it's mainly just taking that tail gas out. We do have some anode recycle that occurs as well, so it'll be taking a percentage of the anode tail gas. With the heat exchangers, we have there's a lot of thermal coupling, and that coupling occurs between the anode and cathode streams. And so this is a kind of a large-scale multi-input, multi-output system, and that is kind of the major challenges. So in terms of the control design, the control architecture, so I'll be focusing, we divide it in terms of the architecture. We're going to have kind of low-level fast control of flows of the flow. Of course, fast is relative, but the flow dynamics would be controlled using servo, controllers, and there would also be then the supervisory controller would provide set points to those flows, and then also would provide set points to any auxiliary heaters. Provide set points to the speed of the compressor expander, and then also set points for the current drawn from the inverter. The supervisor controller would use measurements or inferences of temperatures within the fuel cell, and of course at the inlet to the key rotating machinery. Utilization, hydrogen or steam to carbon ratios, and of course power and voltage on the inverter. So the main goal of the control is to meet a power set point while managing constraints. And of course, we're going to have thermal constraints, utilization constraints, steam to carbon ratio, and voltage that we'll have to be meeting. Our approach for the supervisory controller is model predictive control, and so we develop the model using GPROMs. It's a modeling software, I guess in the same vein as SimScape and Simulink. We have tuned this model using experimental data. The electrical chemical part of the model is really tuned using steady state experiments, but it's the thermal response, the thermal components that are mainly tuned from experimental data. Once the nonlinear dynamic model is tuned, we do linearizations at different operating points, and so the model predictive controller is going to use a gain scheduled predictor, in which we'll have many different linear systems that are accurate at different operating points, and we'll estimate what the current operating point is. Now this of course the operating point changes in time, changes in the past. So this actually will provide it'll provide I guess initial conditions for all these linear predictors, and it'll also provide a mixing, and the mixing will change depending in time. So what we get out, maybe we can consider a linear or parameter varying model. So it's not any one of these linear systems, it's a mix of these linear systems that's mixed over the past and future trajectory. And then that'll provide our predicted output. So of course, at a particular operating point, we can see that the linearized models follow quite closely with the nonlinear model. So in this case, the linear is in blue and the nonlinear is in red in the response. So this predictor is integrated in with an optimizer to produce our model predictive control, which most people are probably quite familiar with. In generating the predictor, so one thing that we're utilizing, so from GPROMs, the GPROMs can directly give us a linearized state space model. So currently we have 11 inputs, 13 outputs. It's a 1,000 state model. So it's quite large, and actually it's numerically ill conditioned, so it's quite difficult to work with in state space form. So we've actually had trouble deriving an estimator using the state space representation, and so we find it much more convenient just to go directly to impulse response representation. So we can represent our predictor at a single operating point, using Topless matrices that incorporate the impulse response. So if we were trying to predict a future output trajectory, we have the convolution of the future input with Topless matrix, convolution of the past input over that fixed time, and then the estimator. We have an estimate of the past disturbance and a past equivalent input that will capture the response in the future due to past inputs. So we're using a past window of 40 minutes to predict 80 minutes ahead. And here's an example where the output here is the cathode outlet temperature, and we have the airflow, air temp, fuel temp, current, and hydrogen flow. So this is our lab. This is the lab system. So it's a slightly different inputs than we would see in the complete integrated system. But we can see how. So this is the predictor, or the actual cathode outlet temperature is shown here in blue. So this is kind of during a startup process. So we've heated up to above 500 degrees C, and we're just starting to increase the current and increase the hydrogen flow. So in this case, it's non-carbon. We're just running hydrogen. The predicted temperature in the future is shown in red, and here we split up the contributions of that future temperature by input and due to the past. So the contribution, so this is the natural response is shown on the dotted green. So that's due to past inputs. That would be mainly due to the changes in fuel and air temperature that occurred in the past. The current point is this point here between the blue and the red, and then the red line shows where the inputs are in the future. So we can see the current is increasing. So the current, the contribution of that temperature due to current is the biggest part of that, and then the other inputs are shown here. I guess we actually I take it back. There is methane, which is also being flown. It's just not listed in this diagram, and we can actually see that the methane causes some cooling due to reforming, which is occurring. So here's some validation of the predictor with various perturbations. So we've got perturbations in the fuel temperature, the air temperature, and then here we've got perturbations in current, as well as fuel and air were adjusted a little bit as well. So here we have predictions 10, 40, and 80 minutes into the future. So we can see, the 80-minute prediction, especially during startup, has a little bit more trouble. But then as we get closer in time, the predictions become much more accurate. We don't have we don't have a lab. We don't have data of the controller, but we do have this is the result of a simulation of the controller, so this is controller. This is running against the simulation of the integrated system, the integrated fuel cell and engine. So here, this is a simulation of reducing from 90 kilowatts to 30 kilowatts. So the set point is the dotted line, and the actual power produced is the solid line. So we can see that on the red dotted lines are the constraints that we are applying to both inputs and outputs. So we can see the response. The fuel is decreased. The current is decreased. We do have supplementary heat, which is being required. And the main reason that's being required is that the anode outlet temperature decreases quite a bit. So we can run up against the lower limit of our constraints on the anode outlet. And so we have to heat the fuel cell, of course, where that's being provided by the cathode heater in this case. We also have limits on the utilization we have to pay attention to that are being active right there. And so that completes my presentation. Also like to acknowledge the team of grad students and postdocs at Mines that contributed quite a bit to this work as well. And happy to take any questions.
Thank you, Professor Tyron. I agree with you, because in the past we tried to linearize a physics-based model, and we obtain several states, especially if you have so many inputs and so many outputs. So, but yeah, you presented good results, simulation results. So I think I'm curious to see the mixing function, how you develop that. But maybe let's move to the next speaker. And
okay, sure.
If you can reply to that question after Isaac.
Absolutely.
Thank you. So in the meantime, we can see if anyone else has any question in the chat. Okay, so our next speaker is Mr. Isaac Frampton. He worked in power industry for 18 years, with Kohler for 16 years. Isaac has been working for 4 years in the Advanced Development Research Group, primarily specialized in control systems and power electronics. So Isaac, whenever you're ready, please share your screen and you can start your presentation. And thanks for giving a talk at the LEAP workshop.
Okay, did that work? Sharing the screen, that is?
It's loading. Yes, we can see your slide. If you can go to full mode.
Okay, so I put it into here. Okay, hopefully that worked.
Yes.
We'll do laser pointer, but I don't think we are going to need it much. Okay, so this is probably going to be a little bit different take on control systems than we're used to from academia, because this is more of the practical point of view of how are these things implemented. So I've been working with Professor Tyrone for quite a while here, and we've been deciding what is going to be handled by the MPC and what is going to be handled off from the MPC. So a few things, and I think everybody's familiar with one extent or another to this, so I'll go over it pretty briefly. But some systems are easy to control and some systems aren't. Like, so some of the examples I've given here is, like, for example, if you're controlling the speed of an engine, that poses certain challenges, but certainly not the same challenges as trying to control, say, a pogo stick. Which, as an example, would have many different actuators that you as a human on the pogo stick could potentially use to control your motion, some of which may interrelate with others. So the example here being, turbochargers being nonlinear systems do behave significantly different than, say, an internal combustion engine, as shown down here as part of a generator, which would behave much more linearly. So basically, each system needs a different control system to control it. Additionally, things to consider are the response times. Like some systems respond quickly, some systems respond slowly. Examples would be, a very, very large engine versus, a semiconductor switch in a piece of power electronics. Very significant difference in how quickly they respond. And then finally, how durable is the device? In other words, how critical is a control mistake? Anyway, if I can figure out how to make this go to the next page, there we go. So just as examples, there are many different control tools available. So, I mean, in this meeting, we've mostly been going over model predictive control. I think model predictive control is extremely valuable, especially for these complex energy systems. And I think it's going to be the wave of the future, but it does have a few drawbacks to it as well. The biggest one being computational complexity, right? It's quite difficult to solve an Mpc algorithm, especially one such as the one that Tyrone is solving with as many states as he has. It's very computationally complex. So this is not something you're going to be running at 100 kilohertz, like the switching frequency of an inverter, for example. You won't be running that algorithm at that speed. So basically, this is a very simple PID shown here. And then, we can go down through the list. State space can give you capabilities that a PID can't give you, still give you some solvability. You can take a PID and put some form of model prediction, a very small amount of model prediction, or maybe a feed-forward table like is commonly done in automotive. That can potentially get you better performance than a simple PID can. And then you can also go into different states where you actually change the behavior of the control system based on certain characteristics of the system. And then finally to full model predictive control. And this listing is mine. This isn't, like an industry standard listing, but in my mind, this is in order of complexity and also in order of difficulty to intuitively understand the system behavior. Intuitive understanding of system behavior, as touched on by several other speakers earlier, is key for humans who will be operating the system to understand how the system will behave. So it is important to have a system that behaves intuitively. And then finally, one thing I wanted to bring out, and this is really important to me working in industry, is that design decisions actually have a very large bearing on control complexity. For example, what I have drawn here is an actuator for a wastegate on a turbocharger. The turbocharger control becomes a lot simpler electronically when it has a mechanical actuator, such as what's drawn here, that controls quite well, actually, the output pressure of the turbocharger by controlling the airflow through the turbine. And for this particular application, that isn't necessarily applicable, but that little actuator actually does a lot for simplifying the difficulty of the control of a system using that turbocharger. So simply because it helps to eliminate chances of getting into surge conditions, and it also helps to eliminate damage to the piece of equipment due to say overpressurization, reverse flow from overpressurization, or similar, like I said, surge conditions. Anyway, self-regulating systems are excellent. And then also just another example would be operating well below what the component's capable of. Like this would be a common thing that would be done in the semiconductor industry, is to say, well, this is a very fast responding system, but if I operate it well below what it can actually handle, the likelihood of damaging it goes down. So the criticality of the control also goes down. Let's see if we can go to the next page. So just as a quick example here, to throw out here that's also important is how well does the control system need to perform. So what I have shown here is a lawnmower. Everybody here has probably mowed grass at some point or another. The idea is when you get into tall grass, the mower bogs down. The mower doesn't really speed back up till you get out of the tall grass. Nobody really notices that it bogs down. Nobody really cares that it bogs down. But if you contrast that with a generator, if the generator bogs down and your lights get dim, you don't like that. You want the generator to stay running at its rated speed. So the reason I contrast these two is because the control system required for a lawnmower is typically just a mechanical lever arm that has a fan that blows air on it that basically works against a spring to keep the engine speed somewhat constant. I mean, these things are super simple, and that works fine because the requirements are low. But on the generator side, not the case. People want a much more complicated control system. On top of that, and I don't want to spend a lot of everybody's time on that, but and like a simple diesel engine that you just change your injection quantity is a lot easier to control than, say, a spark ignited engine with a large intake volume. And that even may be easier to control than, say, a turbocharged spark ignited engine that also fills, say, an intercooler volume or something with the air fuel charge, just because it adds additional delay to the system control. And then finally, I did want to bring out here, also on a power electronics standpoint, you can have a very simple control system, such as the very simple H-bridge shown here to the left, or you can have a much more complex control system, such as a residential inverter that Kohler builds. This is out of one of our patents. Very much more complicated product. Okay, so you can control them both, but the control system for the one on the right is much more complicated than the control system for the one on the left. All right, see if I can get this thing to go to the next page. So finally, and this is the practical consideration slide that we have worked very hard on this Integrate project with, is what can we execute in? So, this is a picture of a computer on the right and a picture of a little microprocessor on the left. Computers work very well for solving very complicated problems very slowly. Microprocessors work well for solving very simple problems very quickly. And so it's a matter of distributing the system in such a way that the high-speed response loops, which was alluded to by Tyrone earlier, are handled in the high-speed components, and that the low-speed control loops are handled by computers similar to this, or at least having similar processor capability to that there. Things to consider: cycle time, how much delay is in the feedback, and how quickly does the actuator respond, etc. All those things make a difference. If you have a very slow actuator, there's no point in having a fast control system. And then, so finally, and this is the summary where we're tying it all together, it's my belief that modern systems will become more of a hybrid type system. I think MPC will be taking over based on what I can see, but it will be taking over on a high level perspective. I think we're never going to get away from simple PID controllers, etc., on the low level, and the simple reason for that being response time of some of the low level systems. So what we're doing with the Integrate program is, for example, we're controlling a lot of the, say, the airflows or the motor speeds, or even like the current from the fuel cell is all being controlled by secondary control systems that for example, in the case of the current, that control system is actually operating at 400 kilohertz to control the current, but the MPC is still operating at probably somewhere around 10 hertz, sending a target to the current control. The current control is controlled very well, and it is still updated by a system that understands all the factors. So we basically, in that case, get the best of all worlds. And I think that summarizes what I had to discuss. Does anyone have any questions?
Thank you very much, Isaac. This was a great presentation. And I would like to open a discussion. Dave, can we have 5-10 minutes for an open discussion?
Sure.
We're a little bit over, but I think we had great presentation. I want to thank everybody for giving a talk at the LEAP workshop. It was amazing. So I see a couple of questions for Professor Tyrone. I don't know if anyone else has question for Isaac. Please send your question in the chat or unmute yourself and ask the question.
And so while they're thinking, I can respond to the question in the chat. So we're currently, in terms of control implementation, so we're currently implementing model predictive control for the lab or the test rig. So we have a test rig at Mines that will run or test the solid oxide fuel cell by itself. It's in a pressure chamber, and you supply it the gases, and then but it runs by itself. So we're actually implementing that. We should have, and we don't have results on that yet, but we should have results within the end of the month. So that's pretty near term. The development of the full system will be occurring over the next year. I think one of the things that I'm very worried about is verification and validation and verification. So it's taking the concept and actually implementing it. So we'll be putting a lot of effort into hardware and loop simulation, and trying to and working closely with the rest of our team. We have a really great team, at Isaac at Kohler, and then a great team up at CSU, and kind of working as a team to process through the implementations. We do simple things first, and then build up implementation that once we get comfortable with it.
Thank you, Professor Tyron. I have a quick question for Isaac. You mentioned an MPC, and then you described a sort of cascade configuration where the MPC is, say, in the other level of PID. Do you see an implementation on ICE or internal combustion engine? Let's talk about standalone in this case. Do you see an opportunity for that, or you think the PID or feed-forward tables, lookup tables would stay on?
Well, it's my belief that as we go into hybrid systems, it's going to become more and more necessary to consider more factors when making a decision. I think the automotive industry has been resistant to MPC simply because of the complexity of the control algorithm and the added cost to their high volume product for the high powered processors that would be required to do it. But I think that going forward into the hybrid space and potentially then into the electrification space afterward, I think it will become imperative. At some point, it will become impossible to control the system with feed-forward tables only. Especially that comes to pass, especially when you have multiple power sources and multiple power sinks. The control is no longer linear. In other words, it's not deterministic from a certain point downstream, like the engine creating the power, the drivetrain consuming the power, etc. It is now the drivetrain could potentially provide power to the engine, for example. That makes it extremely difficult to use a linear control system to handle it. So my expectation is that the linear control system will never go away in automotive, but I believe that there will have to be some form of high-level supervisory control, which I would expect to be model predictive control, that will have to take over at some point. And I would say power systems in general will be that way, for hybrid gen sets as well.
Okay, thank you. Thanks a lot for your answer. Anyone else have any question in the audience? Professor Lima had that. Okay, Harry?
I have one for Isaac. Isaac, great presentation. I just wanted to know from your industry perspective how, because you were talking about control viability, how is testing and validation of the control strategy, if you think it's critical or for the viability of the control strategy, or have you seen that improve design or the development process of the engine or the hybrid system in this case?
Well, I know that the industry as a whole is moving toward using a model-based design and process. I mean, pretty much everybody in the industry at this point does model-based design. The key being getting to the place where we can discretize components to the place where, you say, well, here is this component and here is the controller for the component. And we are going to validate that this component does what the controller tells it to do in all cases. And once this component is validated, we can now do our total system model predictive control validation largely in the model world, because we validated that each component and actuator works within the constraints that it must work within. And I think we can move forward with that. I think that the automotive industry is well ahead in using models for developing pretty much everything. That said, I think that, the energy industry is a little bit more conservative than the automotive industry, and there will always be testing. There will be physical system testing, but it's very difficult to have a comprehensive test suite of a physical system that you don't want to damage. So there comes a point when the model-based control system development is necessary in order to test cases that would actually destroy the physical system. And I think as we go into energy-based systems where we have multiple sources and multiple sinks, that becomes even higher imperative, that we have to be able to trust the models and test with the models. because much of that testing is destructive. If you were to actually run the physical system to those extremes, you would damage it. Largely, in most cases, irreparably. Like you would need to build a new system to further test, and that is cost prohibitive.
Okay, thank you.
And yes, I would just add to that, because in the second phase of the LEAP workshop, the biophysical modeling piece, we're looking at what you point out of how can we model systems and components in a way that we don't destroy and we can still develop controls and study system integration. So yeah, it would be nice if you could be there and see what we're working on as NETLNAs work in this field. Thank you, Isaac.
Thank you, Harry. The cyber physicals workshop starts tomorrow. Actually, it's one workshop. Nana will correct me. It's the cyber physical track will start tomorrow, and we'll end on Friday. So we have a couple of days where we are discussing about how to test controls or other things without damaging equipment. So anyone else has question? Maybe for Mike, we didn't ask a question at the end. I don't know if you are satisfied with your previous question, or you want to ask additional question, Mike or Dave. You have a question for Mike?
So Paulo, it is kind of lunchtime / dinner time for everybody. Our final session will be starting in about, I guess, 45 minutes. So
45 minutes. Oh,
so
I
would encourage everybody after their lunch / dinner / breakfast break, whatever they happen to be taking, to participate in the last session, where we would like to capture all of some of these ideas and comments, and that'll be useful for putting together the final report. And also it's an opportunity to ask questions of some of the speakers and presenters, and even the folks who didn't present but are experts in the field. And then, finally, starting tomorrow, we change focus. I mean, our focus for the last 3 days has been advanced system integration. Our next focus for the next 2 days will be cyber physical modeling, which will include cyber physical systems and hardware in the loop simulations, model in the loop, all that good fun stuff. And focus primarily on technology development. So with that, thanks.
Okay, thank you. Thank you
very much to all the speakers for this session. It was really exciting. I can tell everybody's passionate because they want to just keep talking, right into the lunch break, and that's great. So
dinner break for Europe.
Huh?
And dinner break for the Europeans.
That's right. So Mario, Luca, you guys can have a short dinner break, and then hopefully after dinner you can relax and come and discuss all of the things that have been going on here. So what I'll do is I'll ask Brian to put us all into breakout rooms so we can have discussions. You can pull down on the breakout room. It'll show you all the rooms, and you can choose where you want to go after he distributes us. But then that gives us a chance to to talk in smaller groups while we're taking our break. Otherwise, we'll see you all back here in about 42 minutes. So thanks very much to everyone for your participation.
Okay, so just to let everyone know that this workshop is considered as open to public portion in our decision. It is publicly available before this meeting, and if you will show during discussion and make sure that all the information included in your presentation is publicly available before this meeting as well. And also, this meeting is recorded for the technical node development purpose. And we will send you or a copy of the technical note when it's available. And so in this session, it will be mainly the open discussion and come up with summarize all the sessions and come up with a conclusion report. And Dave is leading and chairing this session. So that's all. I will just go back to this page, Dave.
Okay, thanks, Nana. So I just wanted to leave this up here so we could kind of review the sessions. As I kind of said in the last session, this is the end of the Advanced Systems Integration sub-workshop, I guess, and then tomorrow starts the Cyber Physical Modeling workshop, which will be actually chaired by Professor Mark Bryden during those 2 days, which of course will be really exciting. So I kind of wanted to just kind of review what I got out of it, and then I'm gonna let other people ask questions or talk, engage in discussion. So I think that from a global perspective, you know, all the governments are proceeding towards this whole idea of a net zero carbon, total economy, but certainly the first thing on the list is net zero energy production. As there's more renewables on the grid, certainly there's more transients that we have to deal with in terms of intermittent load, and that's going to put pressure on developing new technologies that can deal with those loads. We've explored advanced integrated systems as being a solution, essentially hybrid power systems, and talked about how they fit into microgrids. And the commercialization efforts that are underway that are being sponsored by ARPA-E and by other industries. So I wanted to kind of open the discussion, getting some feedback on what you thought. So Peter, I know you asked a lot of questions, so I was hoping to get your insights and see what you had to say about your experience here, if you're available. Or Peter Baldwin. Okay, maybe he's still munching on a sandwich. So so Professor Min, are you online? I just don't want to unmute, huh? All right, so how about Dr. Maloney? I know you've been listening in. Maybe you can get us started. So am I talking to myself? Can anybody out there hear me?
I can hear
Dave. We can hear you.
Yes, Dave.
You can hear me. You just don't want to talk. Okay. All right. Well, how about Harish? You participated in the whole event. So are you available? Can you give us some comments?
Absolutely, Dave. I can definitely learned a lot in these few days, and I have a few comments as well. So my background is a little different from many folks here. So I come from a power conversion systems background. I've worked on data center electrical systems and DC distribution systems on ships and power conversion aspects of these things. So the few comments that I did have was that, like you were saying, a lot of push in industry is coming from sustainability mandates and standards from various governments. And one of the important things is to find the right applications where these technologies can be used. One industry really that is kind of leading the way is marine. There seems to be a lot of work that's going on in marine. In a few of the sessions we had here, I think a couple of folks mentioned Fincantieri. they were also speaking at a recent ship technology symposium, and they were really talking about how fuel cells and hydrogen really is the only way for them to reduce emissions in a big way. And so the focus there, it's an application where really the other options are not so attractive if you have to go to reduce carbon emissions. So ABB also has some work here in marine, and we have a memorandum of understanding with Ballard working on some marine applications as well. So that's one point that I wanted to bring up. The other things that I learned here was really about CHP and on hybrid systems being able to really provide the efficiency and the ramp time for stationary power applications. It looks like there is a lot of promise there, and again, finding the right application there where these technologies can be used would be great. The other really insightful session was about the hydrogen embrittlement in pipelines. I think it was a bit of a shock to hear that really this can be a large there can be a large cost issue if there is some sort of transportation of hydrogen that needs to be involved, and this can really upset the equation if it's really that if it is a big issue to move hydrogen, and then these things have to be really considered when implementing some real world systems. So these are all just a few points that I jotted down, and I'm happy to hear more if other folks have opinions on these things. Thanks, Dave.
Thanks for giving us your insights. That was great. So does anybody have any other comments, responses?
Hi, Dave. This is Harry. I think my comment from
Harry, could you go ahead and introduce yourself?
Yes. Harry Boni Alvarado, a graduate student from Iowa State University, working in the Ames laboratory. I work with controls and cyber-physical modeling with Professor Mark Bright and Paula Pazzini. And from the discussions that I've heard this week, from the renewable energy, the hybrid system, and even the existing plans on the control side, I would like to see there has been a lot of model-based approaches, Mpc, PIDs, but most of the challenges that I saw is that integrated system is going to be the way to go. And from that point, I see that controls it should be leaning more into more model-free or adaptable controls strategies that can account for that adaptable integrated systems and can still be optimal. So if there can be a combination between that model-based MPC or optimization approach and also adaptability, I see that as a thing that we're going to need for the future in both renewable hybrid system and existing plants as we try to transition into the net zero carbon energy system. That would be my comment, Dave.
All right, thanks, Harry. I appreciate your insights for sure. Okay, so Jason Hissam, I know that you've participated in a lot of these sessions, so and maybe I can get some comments from you. Or not. See, that's the thing about virtual. You can just not unmute and then you're good to go.
So
Hi, Dave.
Yeah.
This is
Go
Ben.
Hey, Ben.
I had one. It sounds like you want open comments and questions. I have kind of a comment and question. I noticed that in the various talks about hybrid systems, at least one of the teams talked about, wanting to have the fuel cell as hot as possible. I believe that was in the 750 to 850 degrees C range, and another team specifically wants to operate at 600 degrees Celsius. And I see that's quite a big disparity. And I'm just curious as to why the very different choices on operating temperature for the fuel cell.
All right, thanks. And that was Dr. Ben Korpening. He's at NETL. He's the team leader for Advanced Systems Integration under the Energy Conversion Engineering Directorate at NETL. So do we have anybody from the from the Colorado School of Mines team, Integrate team online? Okay. So, I guess I'll comment. So what about from the Nexceris team? Sorry, I'm trying to scroll through the names here because I can't just see everybody. Okay, well, I'll provide my viewpoint, and then somebody can step in and correct me at any time, please. But normally operating at the lower temperatures, I would presume would be just because it's the material limitations are not as high. I know that certainly has been a consideration in the past. Your NERS potential is higher, but then generally so are your losses. So going to a lower temperature is a little bit more difficult. Your materials may have to be a little bit more exotic to go to a lower temperature. This is just strictly for solid oxide fuel cells, of course. So the higher temperatures, you don't have to worry as much about what's going on in the cell. The cell will operate. It's a little easier. You can use less exotic materials, but then you have balance of plant material issues because you're operating at 800 or 850 C. So at least that's from my perspective.
Yeah, Dave?
Yeah.
Yeah, this is Randy. And everybody, this is Randy Gammon. I'm the Associate Director for Energy Conversion Engineering, under which Ben and Dave reside, and a lot of the good hybrid work that's being conducted here gets done. Larry Shadle as well. Now, one of the comments that I heard, just to get at Ben's comment there, question, was that they were hitting the high efficiency, high temperature due to the higher efficiencies that they saw. I don't know if they're really done, fully assessing that. It may be what the model, the system model tells them to achieve, but I think you're right, Dave. They're going to battle those material concerns, and that may put a limit on what they're really going to be able to achieve for efficiency, if they're in fact depending on that for the high temperatures for reaching that high efficiency. But yeah, eager to see what they develop.
So thanks Randy, and also because you've been, and I appreciate the support from both you and Ben over the course of the workshop. I know you both participated and asked a lot of really good questions. So and Randy, I mean you were part of the whole hybrids research scene more than 20 years ago. Maybe you could give us some of your insights. Going through these presentations, a lot has changed in 20 years and some things haven't. So it'd be interesting to get your perspective.
Well, it'll be a brief history then, because very soon after I kicked it off, and I did that with Gio Richards, who was here at the time.
So we basically got program interest in hybrids, explained the efficiency story, explained the challenges that we saw at that time, and Westinghouse, Siemens Westinghouse, was in the process of developing a hybrid system, and there was a lot of hybrid model assessments being done at NETL at the time. All showing these high efficiencies, right? And so there's very high motivation to pursue hybrids, and we established interest to develop a hybrid simulator on site. But due to the many things that were being executed in fuel cell work and other work, we had to look for talent, and that's when Dave came on board. So Dave really picked it up right from the start, essentially, and carried it forward from there, with my constant interest, of course, throughout. So not to try to take up too much time here, but a lot of work was conducted in the past. I know this group has established itself largely with a focus on hybrid systems, and much of that, I think, is this is my interpretation from just a little bit of a distance. A lot of it's with fuel cell, solid oxide fuel cell, and turbine type hybrid interest, ensuring that the control stability and physical limits of the various components are maintained. So there's a lot of work in there, and NETL sponsored a lot of external work too, and the various personnel here, I'm sure, helped contribute to that mission as well. So just to bring it to today's context, for me, what I'm interested in. So we spent 20 years, just thereabouts, looking at the hybrid technologies. Again, our focus, solid oxide fuel cell hybrid systems. But it's always good to stop and assess, what we're doing. And that's part of the motivation of this workshop. Get input from everyone. So I think we all understand that integrated energy systems is going to play a role. It does beg the question, though, of course, what does integrated energy systems look like in the future? To support the future grid, and is it in fact solid oxide fuel cells with a bottoming cycle of some sort, or is a different kind of solution going to be available to support the grid? I'll just I don't think this is new news. Our fuel cells, high temperature fuel cell program is not as robust as it was in the past. I'll put it that way, and it's an effort to gain support going forward. At least what I'm seeing from DOE's front, and this is just my perception. I'm not going to want you to walk away with anything more than that at this time. But fuel cells have had a history of development, and they're still in the under megawatt. I'm talking about the solid oxide fuel cell technology right there. Still under megawatt type capabilities in any kind of sense, I think. And I think the vision for impact, the current grid vision, right, is fast track on renewable energy, and so we all know the duck curve and all the impacts there. How fast can the solid oxide fuel cell hybrid anything support that going forward? It could certainly play a role in different areas of the grid, certainly, I think. But it's going to take further industry support to make that happen.
is what I think. And I hope that does happen. So again, I guess what I'm getting at here is, taking a step back after 20 years, if it's in the need to pursue integrated energy systems, what is that? So I hope out of this discussion we can, get it. I'd be happy to get any thoughts from anybody. Are we just too focused on solid oxide fuel cell systems? Do we need to look at other systems that can support the grid, et cetera? So that's just, I'll just leave that as one question. And again, it's motivated by and the constant interest that I have to ensure that we're doing the best we can to support DOE mission, to support the U.S. needs for energy going forward. And I spoke way too much here, so I'll stop. But that's my motivation for listening in.
All right. Thanks very much, Randy. We appreciate it in any case. So I noticed that Isaac did post in the chat with response to the temperature of the solid oxide fuel. So can you go ahead and unmute yourself, Isaac, and maybe comment? Or okay. All right. So I'll say one last thing about that, and then we'll move on. But one thing too is the requirement for thermal integration. If you're running like in the turbine hybrid where you're actually generating power from the turbine, then there's a need to go to higher temperatures because you want higher turbine inlet temperatures to generate the power with. In the ICE cycle, for instance, really you just have a turbocharger, or you have some other means of producing the airflow, and you're generating your electricity from the internal combustion engine, and generally there's cooling of both the air and the fuel, so you probably don't want to be at as a high temperature. That would be one other thing besides the material limitations, which Isaac kind of alluded to in his comments in the chat. Okay, another thing that I heard come up, and I know not just in the last session, but in almost all of the sessions, folks talked about controls. And I know Randy asked a question of Jack, if Jack Brower in his session, if he thought that the controls issue was essentially tractable, or do we have it all under control? And so I think that's something that I'd like to get some feedback from the folks in the audience. Okay, and Isaac says, hey, his microphone isn't working. And so Professor Alex Tsai, maybe you could unmute yourself and talk about that, because I know you're a controls guy, and I know you had a question on the deadline, so maybe you could go ahead and vocalize that.
Yes, hello. Can you hear me, Dave?
I can,
Okay.
and maybe you could just introduce yourself briefly, Alex.
Sure. So I am Alex Tsai, and I work at the Coast Guard Academy, and I work with Dave and some of the people here in this conference on the hyper on the side of controls. So I've had a little bit of exposure to the control side, and I'm very happy to see some old friends here. So hello to everyone. I was curious about, and I apologize because I haven't been able to be the entirety in all the talks. I've been in and out, but I was curious, Dave, and I'm gonna throw this question out there before commenting on the controls. But is there a hard deadline on possibly an actual build of this
So you know, I certainly will open it to comments.
Dave, can I please reply to Alex and maybe to Randy, because we are trying to connect all the pieces in terms of controls together in the ARPA Integrate project. So we're trying to have a first prototype of 20 kilowatts built in the next couple of years. So we noticed a lot of issues between startup operation, warm up of the fuel cell, electrochemical light off, and load following around nominal conditions. So we, in the ARPA Integrate project, we developed a control strategy, a state machine control strategy that can switch controller, or even basically controller from one operational stage to the next one, based on the need of the operational response of the process. So we are trying to get there. We're trying to connect all the pieces together. But yes, and I think that's my point.
Yeah, no, thank you, Paula. I know there's a lot of work in controls that has happened through the years. I know that we've worked together in developing some of these algorithms. But is ARPA having, you're saying within 2 years or so? Is that or a few years? It's not almost like definite, okay, after this deadline?
So Alex, yeah, so there's about 2 years, a little more than 2 years left in the ARPA Integrate program, and then there's a longer in the REACH program. In terms of what is the actual deadline, I mean, that's been set by, well, in the US by President Biden in Executive Order 14008. He pretty much said, okay, you guys have until 2035 to have a carbon, you know, neutral or no carbon pollution or emissions by 2035. So we've got 14 years so there is a deadline. There's a hard deadline there in terms of that executive order. Alberto, maybe you could talk a little bit about what the drivers are in Europe. Are there any hard deadlines that you guys have to face, or is it a gentle suggestion?
Hello. Yeah. So good afternoon, I suspect, for you, all of you. Yeah, I just wanted to step in with a comment on controls that you have been discussing before, saying that there must be a synergy between controls and real hardware, because it's not only a question of what you can do with controls. In the end, a control is an electronic algorithm that runs and tries to drive hardware. There is a lot of constraints to be understood and maybe overcome onto the hardware itself. And so what I refer is, let's say, the way of designing and the way of managing hardware as it has been since years. And sometimes this needs to be overcome. So like, you know, the ramp rates you can allow on some materials, on some temperatures, on some power for the. So these are all aspects that needs to be revisited, because sometimes controls can go beyond, but they are constrained by physical constraints, or, you know, insurance constraints or other technical aspects. And so there is a need of synergy between controls and real hardware limits. And now regarding your question, now for 2035, we don't have the if I remember correctly, but you know, politicians may change their mind. Maybe after this COP26 ongoing in Glasgow, I have a student there, they will decide to have zero carbon in 2025, and then they will change their mind next year. But at the current state of the art, we in Europe, at least in Italy, the hard deadline we have on 2035 is the stop of production of internal combustion engines for cars. This is the current is a big thing for the social life. In 2035, there will be also a big target in decrease in emissions. But the net zero CO2 of the energy sector should be in 2050 here in Europe at the moment. And so I think there are other countries like I don't remember, India stated something like 2070 for this COP26 meeting.
So Alberto, they're going to, what is it? Just they're going to electric vehicles by 2035. Is that what you're saying?
They want to stop the production, which means that they don't want to inject into the market new internal combustion engine cars. But of course, there is all the second-hand market that will not be stopped as is. But I suspect that there will be all policy around, you know, like taxation, property taxation, and things, or emission taxations that will make less and less competitive running gasoline or diesel car.
Wow. Okay. So, I mean, what about all those, you know, fancy Italian cars, right? The Ferrari and Lamborghini and all those. Those guys are just going to go out of business, or?
They started doing the hybrids, and I think the first Ferrari full electric was launched recently. I'm not don't remember, maybe last year or this year.
Okay. All right.
But I think that the most performing electric car is from Arnold Schwarzenegger. He had a great electric car, I remember.
Okay. Cool. All right. Well, yeah, that's definitely an interesting target. It will be interesting to see how that plays out. So, all right. And I did I interrupt you, Paulo?
No, but maybe I can follow up with Alberto, because he mentioned, I agree with this point of view that the control needs to be applied, and we need to find the limitation on testing the control on the hardware equipment. In terms of his experience on system integration, I saw yesterday that University of Genoa presented a lot of work on energy storage. I just wanted to have an opinion from him on system integration and this type of constraints, what he found interesting, or some big challenge on that, in that area.
Okay. So, well, I'm sorry, Paula, what was the question you were asking about?
Maybe storage? Can you also follow up on the system integration thing? Because when Alberto says that the control needs to be tested and we need to find a limitation on hardware, maybe that goes to system integration, and then maybe you can share your experience with that.
Okay. Yeah, so certainly that's one of the reasons I keep pushing the kitchen sink issues, but I feel like if you're going to integrate systems, it's better to do so, you know, before they produce the electrons, because there are a lot more options. Of course, that means more complicated controls, but you know, I think we need to keep all those controls guys in business, right? So you know, why not push them for more difficult controls and allow us to do more sophisticated system integration? Integrating thermal storage into a device directly gives you the option of taking intermittent thermal sources like the concentrated solar power, and also allows you to take advantage of constant thermal sources like a nuclear. It's like a small modular nuclear reactor. So
let me jump into the middle of that discussion for just a second there.
Sure.
And reach out to Alberto. Hey, Alberto, I wanted to make sure that you're online for being the session chair of the last session. We have you online as doing the summary of the workshop, and then just continuing to host that through. Paulo follows immediately behind you, and he'll be doing the report out. So it'd be great to have you do that introduction for Paulo, since you know him. And then the next step is Dave and I will be talking, and you should feel free to jump in and share that talking also. But if you could host session 14, that'd be great. See if Alberto stepped away from
Mark, I know I will be there on Friday.
So did you say no problem? I'm sorry.
I think so.
Okay. It broke up a bit on me. So
he'll be there on Friday for sure. So
okay.
Right, Alberto. You can give us a thumbs up if you're having problems with your audio. Okay.
Yeah, Dave, this is Dan.
Perfect. And I thought that being able to be the session chair would be great. So yeah.
All right. Okay. Thanks.
There's a scary guy from the past. What brings you to this, Dan? I thought you'd retired and gotten old and ate oatmeal for breakfast and walked with a cane.
I still eat eggs for breakfast.
So Dan,
I just had a.
Could you introduce yourself? Please, I mean, we all know who you are, but please introduce yourself so we know who's talking.
This is Dan Maloney, longtime NETL employee, recently retired. Dave was gracious enough to listening in. One of the things.
So before we go on, Dan, I'll have to do a little bit better than that. So Dr. Maloney has. He's been involved in this since long before I started here. So he was my initial supervisor when I came here, and he's been involved in hybrids and energy systems for at least 3 or almost 4 decades, right?
Probably 3 more so.
Okay, yeah.
I mean, 4 decades at NETL, but I wasn't working on types of.
Okay, all right. Go ahead, Dan.
But it's just one of the things that I haven't heard us talk about. And I think I mentioned this to you the other day, Dave, and on the break. But we look at the duct curve, and there's a lot of discussion around the duct curve, as if all we have to do is manage through the duct. Everything's going. And we don't hear any discussion about these bomb cyclone events and long-term weather events that could last a week or more. No, based on what happened in New England about 3 years ago. In that case, very close to up in the whole grid, which would have led to death. He had a very bad experience in Texas. So part of the discussion, I think, happen is how much backup power is enough to avoid things. And I think these hybrid energy systems actually have a lot of potential because they're rampable. In and of themselves, they'll provide some of that resilience. But I think somebody needs to be working from a systems perspective. Okay, we need at least, say, 10%, 20%, whatever the number is, on the fossil side, provide that resilience backbone. And the reason that number would be important is that then you know what we're designing around in terms of roughly the size and how much rampability we need, what type of fuel, so forth. And maybe that's not the right kind of discussion for the leap, but I do think it's something that energy scientists, whatever you want to call them, need to be thinking about. And I think we need to interject it into national and global. Policymakers think that you can just solar panels online and it's my 2 cents.
All right. Thanks, Dan. I appreciate it. Okay, so
Hey Dave, if I can just add to what Dan was saying, I think the whole conversation around resilience is going to be very important going forward. I think people are really starting to realize the need, like Dan was saying, to have backup power that can do more than just a few hours. And really, once you start pushing it to days, you really need to have something that can work, and solutions where the fuel is available readily and on site is going to become important again for critical installations like hospitals, for example, and for other critical installations. So there, I think really we have an opportunity in terms of hybrid systems. And in multiple sessions, I've been trying to really understand the startup times and ramp up rates in different technologies that have been presented. And really that's also going to be important if we're trying to look to provide some sort of backup power. And that being said, there were also a couple of comments, I think, in many sessions, in some of the sessions today. I think from Fuel Cell Energy, they were talking about a primary power through hydrogen. And that's a thought for certain types of perhaps industrial applications. And there was also a comment about comparing PV with energy storage with these systems. And there are multiple options out there, but I think the resilience part of it would be really an interesting way to go with many of the technologies that were presented in the sessions today.
So Harish, you think that we need to be able to maintain some amount of dispatchable power, beyond just batteries or something like that?
I think people have to really start thinking about that, because really, if the reliability of the grid starts to reduce because of whatever reason, right, more distributed generation, or in general, if you cannot rely as much on the utility as you can in the past, then really you've got to think of other sources of energy. And maybe one way is just to be able to produce it yourself.
Yeah. Okay. Yeah. Certainly. I agree with you. 100%. Because I feel that the reason for going to solid oxide electrolyzers is so that we can make fuels to store hydrogen in, using carbon. If we're going to capture carbon, then I think we need to use it, and not necessarily sequester it. But that, again, that's just my opinion. So, maybe we could. So Roby, I've seen you in a lot of the sessions here, but I haven't heard from you. I don't know if you're online and able to unmute, but I'd be really interested in getting your viewpoint.
Did you just say my name? This is Rory, or who'd you say?
Well, I said Roby. Of course, I'd like to hear from you too, Rory. Roby Lewis is Roby, are you online?
I am, yeah.
Hey, so you're now like the at least acting technology manager for thermal storage or energy
I'm
storage?
not actually anymore.
Okay, but you were, right? You were.
I was, yes. Yeah,
Okay.
so I guess, my background is, I was a project manager, at NETL for 10 years, and then spent some time at headquarters working with Sydney, who's the technology manager for this area, and then came back. I'm actually now back supporting Sydney as the technical project coordinator for sensors and controls. So I've been listening in. The technology manager detail ended last week, actually. So you're not too far off on that timeline.
So that's why you have time to be here. Right?
Yeah, exactly. So,
cool.
No, I found that, I mean, Dave, just sort of, listening to the conversation, I found it to be very enlightening. In fact, I spoke to Sydney. I had a chance to speak with her after day one, and I was just saying, I think we've worked in this area for a long time. You and I have had conversations in the past where, we've talked about, like, where does this go from here? And I've been really impressed to learn and of what's going on and here you did a great job, I think, of compliments to all the organizers. The speakers really highlight the need for this and the potential for this and a lot of the options that are available to us going forward. And so, I think in the past, you and our conversations have been, about, where does this go? And I think you've done a great job of highlighting the potentials, the value in this. And I appreciate having the invitation and actually being able to, step out of that detail and time to actually hear this conversation. So thanks for inviting me.
No, I appreciate it, Roby. You pretty much always. I know that you've attended some of the other LEAP workshops, and it's always great to have your participation. So, and certainly from my perspective, it seems that when we started, it was all about efficiency, and it was all about base load, and now it's more about distributed generation. And it's more about, which actually is where we started, right? We started with distributed generation. Mark Williams, that was the centerpiece of his program when I first joined here. And then, and now it's resiliency has come up a lot, flexibility, load following, all of that. So, yeah, so I appreciate your participation for sure.
Yeah, thanks again for the invitation.
Yeah. So, and speaking about load following and transient operation, because that's one of the things in terms of the last 20 years we've made a transition. And we started off with fuel cell turbine hybrids, then we used it as pretty much a case, like a case study for developing controls, because it's a very challenging subject for controls. And then we went to hey, now the flexibility that we can derive from the hybrids may be more important than the efficiency. And so, Rory, I'd like to get your comment on that, because I know you started off, at UCI, involved in stationary power generation. Now you're doing, aircraft. So, and that's the ultimate for transient operations. So, maybe you could chime in on what you think the future is and exactly how flexible you think these systems could be. I know you're out there.
Yeah, I'm here. Sorry for interjecting earlier. I thought I heard my name.
No. Well, and I was thinking your name, so you're just a step ahead of me. That's all.
So yeah, I mean, I transitioned from stationary power, to more transportation, aerospace-based propulsion and power and thermal systems. And if you would have asked me before 2012, 2013, would I ever even consider putting a solid oxide fuel cell on an aircraft, I would have said no way, just because of the challenges that were present then, from startup times, just large thermal masses, power densities. There were a lot of challenges at that time. And just because some of the systems that were demonstrated before then that I got to be, luckily I got to be, you know, interact with them a little bit with the Siemens Westinghouse and Fuel Cell Energy. You know, those were demonstration units using off-the-shelf type parts. The controllability, there were some challenges in some of those, and they were, you know, they operated fine, but transient would have been very challenging. So from an aerospace perspective, not only are you dynamically changing the load dramatically, you're changing the pressure and temperature, which that really impacts what your temperatures and pressures throughout the system are, and your mass flow and such, because your corrective mass flow will stay the same, but your actual mass flow through the turbine will be dramatically different. So, you know, with some example concepts out there for an SOC hybrid system, and I presented one, and there's one that we're working on in the REACH project, that if you try to eliminate some of these large components, such as heat exchangers and such, and try to look at the system in a more simplified way, and the way I did that was first looking at how do I increase power density? What do I absolutely have to have in this system in order for it to operate? And with that, I think there is the possibility of having some high power density solid oxide fuel cell gas turbine based propulsion systems. And I think if that can be achieved, then pretty much that type of SOFC architecture could be utilized almost anywhere, because now it's kind of earned itself as a possibility of compressed natural gas or liquid natural gas based SOFC system for a hybrid vehicle. Looking at more of a, not a zero carbon solution, but a very low carbon solution. Because if you start looking at that direction through the efficiency gains and the carbon reduction in fuel, you're going to get a 60+ reduction in carbon, if not more, through the efficiency gains. So it's a substantial change. And plus, you know, here in the United States, is looking at it, we're going to become the largest exporter of liquid natural gas if we're able to get our ports open by 2022 or 2023. So we have tremendous amount of liquid natural gas and methane, and that's where I see SOFCs have a very good opportunity, because they're the most efficient technology out there when put in a hybrid system, especially when you consider methane. Because it's very easily to utilize that. If you try to use liquid fuels and such, and depending on how you do the reformation, you could take a 10% hit in efficiency. With methane, you can definitely gain high efficiency through the, lack of a better word, chemical recuperation. I'm not sure if you have another word for that, Hank, but through the steam reformation, that you're essentially taking waste heat and turning it into higher heating value fuel. So I think that has potential to really add, that's where you really get some of the big efficiency gains you can use in methane. So in short, I think there is an opportunity in the transportation sector and the aerospace sector, because if you really look at the aircraft itself, we're not going to get much more efficient out of a gas turbine engine unless we have new materials development to drive it to higher temperatures. And that is a possibility. But if not, you have to eliminate the combustion process and use something that destroys all the exergy in the fuel almost, or a majority, or 30–40% of the exergy. You have to look at another way to produce electricity on the aircraft if we really want to lower emissions and have an all-electric propulsion system on aircraft. And so there are some possible other technologies out there that do it, but you have to have power generation on an aircraft in order to do long distances and carry large payloads, such as a Boeing 737 class aircraft, for example. Batteries and such are just not going to get there, at least not for any foreseeable future of any chemistries. So I just kind of, to keep from rambling on, I'll stop there in case anybody else has comments, or I don't know if that was the type of answer you're looking for. But.
Well, no, I mean, so yeah, I think it is. And I mean, you did bring up a good point about, you know, natural gas. I mean, the thinking being that on anode reforming is one way to recover is to use that heat sink of reforming, steam methane reforming, in your cycle to gain efficiency. In the Integrate program, we've done a lot of system analysis work that showed that you can get the same efficiency gains by doing external reforming using other heat from other parts of the system.
But that would increase your gas turbine mass flow, and that's a lower efficient system compared to a fuel cell with an overall C.
No, it's not. I mean, so remember, in a hybrid system, it's not a topping bottoming configuration, right? Not if it's recuperated. All of your losses are coming out of the recuperator, right? So it's a true hybrid system. So it's not a question, it's not a parasitic, like in a standalone fuel cell system, you have a blower, and so if you have a standalone fuel cell system, then, you really on anode reforming is the way to go, because you have no other way to reject the heat, and you have no other way to recover energy from the losses. But
yeah,
in a hybrid system, it's a different story. There are a lot of other ways to recover the heat. Now, we've been tasked, Dave too has tasked us with looking at liquid fuels and other fuels to see if we can gain the same benefits, if there are other thermal integrations that will result in the same thing. But what it comes down to is when you do on anode reforming, that's just a thermal integration strategy. And there are other options that you can use for that will give you the same efficiency or even higher efficiencies than on anode reforming, just doing completely external.
That's highly sensitive on the efficiency of your gas turbine or your heat engine that you're integrating with, because if you do not do on anode reforming, that requires a significantly more mass flow for the SOC to thermally manage the delta across the SOC, and that requires a larger gas turbine, which is a less efficient technology in that hybrid system, and therefore you're shifting your power split not more, but a little more to the gas turbine versus the SOC for a given power capacity of the system.
So that's correct, but you're also at the same time reducing your fuel utilization in your fuel cell, and that increases your voltage. So it's an offset. So the best balance though is not the smallest gas turbine, right? The best power split that we found was more like around 60-40, fuel cell turbine. And that's 60-40, and we're still over 70% efficiency on natural gas. And that's with external reforming, right?
Yeah.
So but the thing is we're using heat from other parts of the system. So, in terms of liquid fuels, can we realize the same benefits? Probably, but we'd have to take a look at the entire cycle. So no matter what, you really have to look at the entire cycle to do that. And but that's the other thing too, is that, okay, how important is that? So you take on some extra flow. Well, what if we go down to 50-50? Or, let's say we go to 40-60, where we have 40% fuel cell, 60% turbine. Okay, now our efficiency is down to, 65%, but we have a lot of flexibility there.
Yeah.
Just having the fuel cell in the turbine gives you high part load efficiency that you don't see with a standalone turbine. And at the same time, you've reduced the cost because the fuel cell is developing technology and the turbine is more mature. And both systems, they synergistically provide each other flexibility. Because you have a lot of airflow going through that fuel cell, it's easy to maintain temperatures, right? So just some simple bypass valves, and you can maintain the temperature wherever you want it. And you don't have to worry about temperature gradients because you have more airflow than you need. At the same time, because you have a big thermal mass in your cycle, the turbine has a way to just continually maintain a spinning reserve at a much lower cost. So there are a lot of synergies by coupling systems. But the big question that I had for you, Rory, is because you've been looking at extreme dynamics. Can we take advantage of that instead in essentially land-based systems for load? And is that going to play an important part in the future when we have a lot of intermittent renewables on the grid?
Yeah, definitely. If you're willing to give up maybe estimating in my head, 5 to 8% percentage points for, getting up to about the 65% efficiency on a system like we're proposing in REACH, that's probably the max you would hit with a little bit of recuperation. Not much, but then you definitely, there is a large amount of I guess power shift or transients you can have in the system and still maintain good thermal management of the fuel cell itself. For example, I mean, right now we're proposing different operating regimes, definitely between takeoff and cruise for an aircraft. With an aircraft, we're definitely not that efficient. But we'll have a really high power density based on that power rating we're able to produce. Versus when we're at cruise, we have a really high efficiency and our power went down, but we do have a spinning reserve while we're at cruise of around an additional almost a doubling in power. And basically the system is being designed so that if we were to lose one system, let's say one engine, the other one could provide the power that can recover from both. It just takes an efficiency hit. We could even lose one module of SOFCs because we don't have centralized bypass valves. We can actually operate losing one stack and still maintain 97% of our power output without losing efficiency. And so, but I think that's for reliability, redundancy that's required in aerospace. But for power generation, I think it is. I think it could be very interesting to take a look at this from a land-based system, just because I think it could be much cheaper, and I think it can be a much more simpler system from a control standpoint and much more rapid load following capabilities, because you're not buying the big heavy heat exchangers, the big heavy valves, and those things. So it's a much more simpler system with just essentially a gas turbine, an SOFC stack, and fuel valves. Of course, you have all the manifolding, but there's not a lot of those larger components out there that even if I just look at the heavier it is, the more it costs from a material standpoint. So even just looking at that simple comparison, I think it could be I think there's other opportunities to have much cheaper systems out there that actually provide better response time and better load following capabilities, and even fuel flexibility. If you're able to minimize some of those thermal masses and other things that occur in the system and find a more clever way of reducing it and controlling it, I think you can have better fuel flexibility during transients as well.
All right. Yeah. Thanks, Rory. It's exciting times. So.
Yep. Thanks.
Okay. So, Xiaodong Zhou, did I say that anywhere near correct? I know I talked to you during at least one of the breakout sessions, and I know you had some insights. I know you're itching to share, right? Or maybe not. You're muted if you're trying to talk.
I'm listening. Yeah.
Okay. All right.
Thanks for the workshop. It's really great.
So maybe you can give us some of your insights about this.
First, I learned a lot. Truly learned a lot from the integrated purpose coming from academia, industry, and different aspects, right? And what I think in the future would be make it more diverse and including, for example, expand the path to the commercialization part. And I feel this solid oxide cells are critical element in as you mentioned, net zero or hydrogen production economy, and then add the commercialization elements, and including something as the necessities for supply chain requirements, including more, for example, blue energy. I thought the blue energy would be, they probably don't want to participate, but their perspective will be critical too. What do you think, David?
So yeah, I don't know if we did we reach out to Bloom Energy now? I thought we did. We know the chief technology officer at Bloom Energy. We submitted a proposal with them, but you know they're a little bit more on the you know, secretive side. So
yeah, always
it's easy to get them to participate. But yeah, I think we did reach out to Bloom Energy. But and no, go ahead.
So this happens, yeah, for a company like Bloom or publicly traded companies, and they often come or join the workshop or meetings. They listen, but they don't want. We need their opinion, but they don't want to share their opinions. And this is it's a dilemma. But I think their opinions and will help the community and both the academia and other small businesses or industry, to make the pie bigger instead of struggling for some of the others.
Yeah, that's a great insight. I think it'll be easier in the future when we can all get together in one place. We're kind of limited in how long. So we're limited in these 3 1.5-hour sessions just because we have people from China and we have people from Europe and, you know, everywhere in between. And so it's really difficult to have long sessions, you know, over 12 different time zones. So, you know, so because like the folks in Europe right now, they're getting ready for bed, and
I know
people on the West Coast are eating lunch, and people in China are, you know, maybe getting ready to, well, in a couple of hours we'll be getting out of bed. So, you know, that's really tough. But if everybody can come here, then that'll work out. That has worked out a lot better for us. So.
So next year, you say you plan. This is a great workshop, by the way. This is awesome. I wish I could participate earlier on in previous workshops like this. And this is a great workshop, and I very much look forward to the next one, and probably will be in person. This is awesome, and it fits the FECM and or in general the scope very well. This is exciting, Dave. Very exciting. Truly exciting.
Well, thanks. We appreciate it. So we're going to make sure that you're here next time, especially if it's in person. We want everybody to come back. So
okay,
it's
thank you. You made another great comment, David, and I will use it in my next DOE or other workshop. You mentioned do not let professor talk. If they start to talk, they will use the not only their 15 time slot, they will use the extra time. And you just did it again. And
yeah,
it is true.
Well, I'm guilty, right? I mean, I'm not saying anything that I'm not guilty of. Yes, that's well, professors are. I think you know, Dr. Mark Bryden, who is aside from being director of decision science at Ames, is also a professor at Iowa State University, and he always is saying 50 minutes. We talk in 50 minutes blocks, right? You know, and well, even Professor Massar, though, I say, you know, he's like, what do you want me to talk in 10 minutes? Dave, you're killing me here. You know, I mean, normally I have 200 slides, which he covers in like, you know, 40 minutes. But, you know, so yeah, if you want to, and I often say the same thing. You want me to talk for 50 minutes? I can do that right now. You want me to talk for 15 minutes? Oh, I need a month to prepare. You want me to talk in 5 minutes? Oh, that's tough. So, you know,
Yeah.
we did our best to try to keep it under control. But as you pointed out, we went over. But I think it was good. I think it was exciting. So
It's excellent. Thank you, David. That's my 2 cents.
all right. All right. Well, thanks very much. We appreciate any of the comments we can get. All right. So I know that we're kind of closing in on the hour, but Professor Min, are you out there? Professor Win Min, University of California, San Diego. I know you're online.
Yeah, I'm here.
Oh, yay! All right. I know that we had some discussion about fuel cell operating temperature, and I'd really like to try to capture some of your viewpoints on that, because I know you had some really awesome ideas. But I, you know, when it comes to how to operate an SOFC and what temperatures, thermal integration with heat engines and all that stuff, I'd really like to get your view on that.
Well, as you know that actually right now the SOFC can be operated on a range of temperature from high to low, right? Some recent data that I've seen it now, the SOC can operate at, you know, at around 600, doesn't have to be it. And with a very high performance also. But I think that the main thing is to optimize the operating temperature to get the best efficiency for the hybrid system, right? I think that it's not very much depending on what type of gas turbine you use and the pressure and things like that. So there are a lot of work need to be done for the integration and optimization. I think in general, my understanding is you want to operate the SOC at higher temperature as possible to get the best performance from this for the system. But on the other hand, you know, the thermal management for the fuel cell and the integration, thermal integration play a role in, you know, what is the optimum temperature that you select for the system. So that, you know, I don't know what the, you know, should we operate at high or low? Or I think that a lot depending on the system design.
Okay, so you're kind of of the opinion that you should do kind of, and I'll use the word. I know we're going to talk about it tomorrow and Friday, but co-design both the components and the system at the same time.
Yeah, I think that's very important. The integration of the all the component. But the FLC offer, you know, offer now we can see that you can operate the fuel cell at lower temperature, but you still get the same performance. But is that the best temperature? I think we need to do the integration and thermal management analysis to determine that.
Okay, well that's definitely helpful and certainly leads us into the next couple of days where we'll be talking about designing components and
I think Dave, I think we need to do that. We need also determine whether, you know, the FOC need to be operated at what pressure. Is that fair to do it under pressure? And then what pressure should be?
Certainly, there are some gains for operating under pressure, but then that's obviously diminishes, right? I mean, I know that.
Yeah, I think there's some data reported that if you go over maybe 3 to 5 atmosphere, you don't get much in
Right.
terms of the performance for the fuel cell. But on the other hand, I don't know whether that how you integrate that with the gas turbine. That could be there's some sweet spot that you get the optimum performance.
Yeah, well, certainly if it's a recuperated cycle, then you don't want to go more than 3 or 4 atmospheres of pressure. But well, I think. Well, I know that Rolls-Royce had looked at cathode recycle to avoid using exhaust gas recuperation. In that case, they wanted to operate at a higher pressure. I think a long time ago, GE, they were considering a direct pressurized system at a very high pressure, right?
Right. Yeah. But that for I think that for a very big multi-megawatt system.
Yeah. So.
By the way, I really enjoy the meeting day as usual. I think I attended all the others, maybe not except the first, maybe from the second one, right? And Morgantown. So miss in-person meeting this time, but well thought out agenda. I think it cover a lot of aspect of this technology. So looking forward to the modeling on Thursday and Friday. But congratulations, Spice. And you gather many speakers from on over the world and expert on different area in this. So that's a very, very good, very good meeting.
All right. Well, thank you, Professor Min. I appreciate it. We appreciate your comments, as always. And we look forward to seeing you in person next time. So
yeah, hopefully. I thought that we got to see you and sometime this year, but
yeah, it's I know it's been rough. So hopefully things will improve next year, and we'll be able to see each other in person. So yeah, thank you very much. All right. So does anybody else have any other comments? Please feel free to interrupt. Otherwise, I can just try to pick names out of here to get some feedback from you guys. But so Subir, okay, I know that I know I've seen you participate some already, but it would be good to see if you're out there.
Hi, Dave. Yes, I'm out here. I don't know if you can hear me.
Okay, yeah, we can hear you. Yeah, we can hear you. It'd be good to get your comments because we've heard a lot about fuel flexibility and trying to reform liquid fuels versus natural gas and all of that. So, so maybe you could give us a few comments.
Yeah, sure. So I was, first of all, it was, I was listening intently to all these discussions, and it's indeed, all these things are correct, and in terms of the fuel flexibility, my thoughts are that if you're going to go for the reach effort, for instance, where it's airplane, it has to be some kind of dense fuel, and that has to be liquid fuel. And then with liquid fuel, doing liquid fuel reforming, like you mentioned, with methane, mentioned about the efficiency and the heat transfer and all those things. But with liquid fuels, doing on-cell reforming is still, not very, not well validated for the higher hydrocarbons. Yes, perhaps it might be able to do it with the ethanols and the methanols, but with the higher hydrocarbons, it certainly still poses challenge. And in terms of the integration with the turbine, Rory mentioned a whole bunch of things that I was listening to, and there's a lot that needs to be formed out there in terms of how the system's integrated, what's if it's a pressurized system, how the weight of the housing and all those kinds of things. What is the load balancing between the turbine and the fuel cell? We talked about, there was discussion about part load and full load and so on and so forth. And so there's a whole lot of information that needs to be sorted through, especially in light of the work that you've been doing in terms of trying to sort through some of those things in the integrate program.
So, I've kind of mentioned before that there are several opportunities for thermal integration of fuel processing. So having an external fuel processor, there are opportunities to have the same efficiency by taking heat from other parts of the system. Do you think that's a viable option in terms of the technologies that are available for doing steam methane reforming of liquid fuels?
Yeah. So in terms of external reforming, I think certainly those things could be done, and the external reformer can be integrated with the system. But again, then that there are issues with heat exchange and separate vessels and so on and so forth. That in terms of looking at the specific power for at least aircraft application, it seems like it's just a extremely aggressive target to try to get the specific power with the fuel cells to be competitive with what's needed for flight, especially for large single-aisle aircraft.
Okay, well, thanks so much for your input for sure. Okay, so I know we only have 6 or 7 minutes left, but so is there anyone else who'd like to go ahead and make some comments now, or even just pose questions to the community in general? The idea is to try to capture these and get them put into our technical note, which we'll send out to all of the participants later on. No one, huh? Okay, so I'll try to.
Dave?
Yeah.
This again, regard to the reforming, have we ever considered that you have a direct operation of the FCC with natural gas for the hybrid system? I mean, without a reformer.
So yes, I think that was well, certainly that's one of the goals, I think, in the integrate program, or one that they were looking at, was to try to do as much reforming, probably fuel cell energy, right? That was one of their goals, was to take methane directly. I guess methane and steam on the anode to try to do.
To do inside or internal reforming, or there are other ways to do direct oxidation of methane within the fuel cell. I think it will have significant impact on not only the how you do the thermal management of the system. And I don't know whether you're aware, we have a project with Alpha for the aircraft power system, and we propose that to do a solid oxide gas turbine and battery hybrid system. But the gas turbines mainly provide the compressed air for the FOC, and it may be there's some extra power then. So the FOC doing the mainly the power generation, the gas turbine mainly provide the compressed air and maybe provide some extra power for like de-icing or heating or whatever for the aircraft. So that's a little bit different way to apply the hybrid system. So the thermal management and all the integration is somewhat different from what you use for stationary application.
So do you have to use like inhibitors on the anode to try to get a better temperature distribution, or is localized temperature gradients or are localized temperature gradients an issue?
Yeah. Mm-hmm. And we also want to do without reformer, everything is in the stack, so that for aircraft application it will be reduce weight and volume for the system.
Mm-hmm. Yeah. Okay. Yeah, well, that, like I said, I think that'll be a little challenging on the localized temperature gradients, but if you can get materials that will survive it, then
yeah, that's a challenge. But I think it will going to affect the thermal management and the integration between the gas turbine and the fuel cell.
Yeah, there's no doubt. We've looked at using the hyper facility. We have looked at using now this is with the cyber-physical fuel cell, but we've looked at changing the composition, right? So putting a bypass around a reformer so that we can play with the balance of hydrogen and methane in the stack to do thermal management in the system. So so yeah, I think any research in that area is going to be very valuable, especially direct electrochemical oxidation of methane. That's something that's we haven't really considered, right? At least not to any appreciable extent that I know of. We've always looked at, okay, we're going to reform it first and then shift it and then oxidize the hydrogen mostly, and CO to a much smaller extent. So
I think if you do the direct electrochemical oxidation, the thermal management, the integration, system integration is somewhat different from what
no doubt.
System.
No doubt. So, all right, Professor Min, thank you so much for the discussion. And I think that we're just about out of time. Is there anybody have some last comments or questions? It's hard for me to see the hand, so just unmute yourself, please. And
this is Bill. Can you hear me?
Yeah, we can.
Great. I just have some sorry about that last minute thought about grid resiliency and flexibility. So personally, I don't think grid scale energy storage is a viable option, because if you read some independent report, you can see their operations largely depends on government subsidy, and if without the government subsidy, their payback period is even longer than their lifetime, and they have safety issues, and they largely depend on the real Earth elements that is a potential risk for national energy security and the supply chain. But if you look at what we recently did in our lab, we achieved 50% turn down and the following ramp up in 10 seconds. Please note, this 10 seconds is an arbitrary value, and after, if we develop the automatic control system, we can again reduce this 10 seconds time window to maybe 5 or even 2 seconds. And we can be the game changer to provide great flexibility to support great resiliency. Or alternatively, we can integrate some like small scale co-located energy storage. We are not talking about like hundreds of kilowatt hours. We are talking about serial 2 or 5 kilowatt hour. Actually, we already considered that early this year. We integrated a supercapacitor to our hybrid system, and we can do instantaneous response.
The meeting on let me.
Sorry, go ahead.
Yeah, we integrated a supercapacitor to our hybrid system, and we can do instantaneous response to the step change in grid demand, and that's awesome. And my last thing is, I also agree with Dr. Randy Gammon. Like we have been doing this integrated energy system research for the past 20 years. We do reach the point like we need some kind of demo. So personally, I think after the SRFC GT Siemens Westinghouse system at University of Ireland, after that we didn't hear about like very successful demos all around the world. LG said they did, a Japanese company said they did, but we didn't see much open publication or report. And personally, I would say, I think like the whole IES community should work together, both academia, industry, national lab. We should set a demo to show to the world, like IES can change, can provide the support they need and contribute to zero carbon. Just the sort.
Okay, all right. Thank you very much, Biao. Was there a response to Dr. Zhang's comments? I thought I heard somebody. Okay. Okay, well, going once, going twice. Okay, so with that, we'll go ahead and end this session, and we look forward to tomorrow morning, especially me, because Professor Bryden will be running the show. So tomorrow, I will still be there, of course, to support him, but he'll be chairing those sessions tomorrow and Friday. So thank you everyone for participating in this event. I always learn a lot, and I really appreciate all of the participation and the effort that was put in by the presenters. And so thanks very much.